We'll give you a 5 minutes warning, which will be after 35 minutes. So if you talk for 5 minutes after that, you will have 5 more minutes for questions. If you talk for 10 minutes, there will be a rest. And we count in a quarter of an hour.
So maybe you could say a sentence why I was late, you know, that, otherwise it's very impolite.
Thank you. Good morning, everybody. Sorry for the delay, but the people coming from the guest house were involved in a car accident, and that provoked this 15 minutes delay. So we start with 15 minutes delay with Peter Zoller, who will talk about quantum simulations with atoms. Please.
Thank you very much for the invitation to come here. I always enjoy going to these interdisciplinary conferences. Can you hear me? Or? Okay. I always enjoy coming to these interdisciplinary conferences, and I guess that this is one of them that really tries to combine quantum gases, or condensed matter physics, fundamental interactions, and cosmology. So I'll be speaking about quantum simulation with atoms today. And my talk will consist of a very general global introduction. And then at the end, I would like to focus, or maybe in the middle, I would like to focus, on really new things that we're doing at the moment, and present some very recent and also some new unpublished results. My own background is atomic physics, quantum optics, but I would say that this field has been really dominated for the last 25 years by becoming interested in controlled quantum many-body systems that we can build with these atomic systems. And I've listed a few down here. We came up with proposal for trapped ion quantum computing, optical lattices. This gave rise to major experimental developments. Very recently, also the Rydberg arrays, also done with Rydberg atoms here in Pisa, polar molecules, and all of these photonics devices and so on. So let me sort of upfront say, what we are interested in, the reason why we want to do quantum simulation is, of course, related to the fact that if you do quantum many-body physics, we have entanglement. Entanglement means that if you got some, say, spin system, to just write down here one example, think of magnetism, quantum mechanics tells us that it's not like in classical physics that we are cycling through the various microstates, represented by these configurations, but rather we have a superposition of all of them, and these can be exponentially many. And when we give talks to our high school students, for example, we always say that simulating 300 spins, if you look at the Hilbert space, assuming that the wave function is really so big, requires building a computer that uses classically every atom of the visible universe as a memory cell, and clearly this is something which is unreasonable. In reality, of course, very often the states if we talk about here can be compressed, but we'll be interested in the end in the situation and also quantifying that, where these superposition states hopefully will be very large. So this is exponentially large, and then Feynman, of course, is one of our saints that we have in quantum physics. Said a long time ago, it's difficult to put, of course, these things because of that reason on the classical computer, so we should actually build quantum devices, and that's what we do at the moment. So let's build then quantum devices, either as quantum computers and maybe quantum simulators, which are sort of specialized to treating with certain many-body problems that are kind of new kind of condensed matter physics. And the question is how to do that. And this is the point where we are coming in with our proposal. But let me sort of remark up front, you might say, when it's all of these things interesting, the point is really that at the end of the day, of course, our goal has been to outperform classical devices. And maybe some of you have seen that Google announced quantum supremacy yesterday for a problem that was sort of very artificially constructed, but it's a very interesting result that they have. So I put on here, outperform classical devices for a relevant problem. And this is really what the goal is. We would like to do something that at the end where these things are really useful, and not only demonstrations of the capabilities of the devices that we are building here. So what's the reference point? The reference point is, of course, that in quantum information over the last, again, 20 years, significant insight was obtained by classical simulation, and very often they consist, matrix product states is sort of one example, PEPS in 2D, this is 1D and this is 2D over here, MERA. By using, for example, in the case of the matrix product states, simply a Schmidt decomposition over here, and then cutting off these expansions at certain points that illustrate what we call the bond dimension. And so very often the states that we have, and this is very often true also for the ground states, they don't really live in whole Hilbert space, they only live in a relatively small part of the Hilbert space. Of course, things get completely different if you started looking at, say, time-dependent dynamics, quench dynamics, and all of that, because in that case, what you have is that the wave function can really sort of, entangle a very large number of quantum states that we have. And this is, I guess, where really ultimately quantum simulation is coming in and is actually developing its power. So coming back to the question, when is it interesting? I would simply say that when all of these techniques that we have here classically actually fail, and quench dynamics is one example, and you will afterwards see examples where we will not be able to claim that we have actually quantum supremacy or a quantum advantage, but it's very clear that we are doing something where we got very large entanglement, and we will also be able to measure it. As you can see, we will develop certain kind of protocols where we can determine these things experimentally. Let me sort of give you a very brief and very qualitative summary of systems that we looked at in this context. And many of these proposals from our side, the theory side, are now maybe about 25 years old. We proposed, for example, trapped ion quantum computing, where you do what we call a quantum logic network model. You have a set of qubits, operate with gates, and in principle, this allows you to construct any quantum state that you want. Based on just applying unitaries that you decompose into these quantum gates that are single qubit gates, gates that might entangle 2 or maybe more qubits. And this framework has been used now in the past for demonstrating some simple quantum algorithms, so usually for a very small number of qubits, because we got, of course, decoherence in this problem, requiring ultimately error correction, all of this, and this is where the whole thing, of course, will explode. I note that we in atomic physics have a significant advantage in this context, because our qubits, our two-level systems, they are actually, in terms of quality, very good, and the reason is that, in atomic physics, we built what we call an atomic clock. You heard a talk yesterday mentioning these things, and you could see the fantastic, long lifetimes of these quantum states which are used in this context for the atomic clocks. Just take this argument and put it over here. That's the reason why atomic systems are sort of so great for building these kind of things. On a completely different side, there's quantum simulation, what we call analog quantum simulation. Again, we came up with ideas like building optical lattices, where you take simply a standing light wave of lasers, you put the atoms inside, say both Einstein condensate, maybe called Fermi gases. By making very deep potentials over here, you can see that this becomes a lattice models where atoms can hop from side to side. If you make the potential very high, the hopping will be slower and slower. So this means that the kinetic energy can then be much smaller than the potential energy, where all of a sudden out of a Bose-Einstein condensate, which by definition is a weakly interacting quantum gas, you eventually get something which becomes a very strongly correlated system. So one is after strong correlations here, which also means then large entanglements. And one example that I put here is the Fermi-Hubbard model in 2D, as sort of a toy model of say, high TC. This is one of the holy grails. It is very easy to engineer the corresponding Hamiltonians in our context over here. What is actually very hard in the experiments, and this may sound like a joke, we have maybe 10 nanokelvins or so, that the temperatures at the moment, if you would like to see the phase diagram with this antiferromagnetic phase, the superconducting dome with the D-wave superconductor here, one is roughly up here in terms of the temperature. So one can see some of these phases, but the really interesting thing will start down here, and one is not there yet. So it's a temperature problem. It's not the problem of realizing the right Hamiltonian. Let me sort of make the connection here, between this optical lattice, say with fermions, and what we do with real materials. When do we go to the quantum regime? Well, when the wavelengths that we have, for the given temperature, when the wavelengths that we have here is comparable to the distance here, we would like to have this inequality over here. And if you take ultra-cold quantum matter, like the ones where we build optical lattices and we put atoms inside, the densities are actually very low, and the scales, of the say separation is something like of the order of 1/2 of a wavelength, so it's a few hundred nanometers, which is huge. If you take real materials, the density is very high. Distances between these atoms of the electrons hopping from one ion core to the other one are much, much smaller. But what really counts is the fact that lambda over d, a dimensionless parameter, is really the same in both of these. The main advantage is that over here we got a system that we can control optically. We can shine lasers on individual lattices. We can read them out. So these things over here become sort of a toy implementation of real materials, where you pick out certain parts of the Hamiltonian you would like to understand, you can control them, and then even watch them. And one of the recent advances in this context over here has been what's called the quantum gas microscope, where one is able to look at individual atoms. And you can see here, for example, these are processed images of atoms at single lattice height with spin resolution, this Hubbard model, showing very nicely that you got, for example, antiferromagnetic phases and all of these kind of things. You can see that every second one, is sort of spin up while the other one is down. So this is seeing the antiferromagnetic phase, really live under a microscope, and these are single shot images of these atoms that one is able to do. So you can see that here we have the world of quantum computing. Here we have sort of quantum many-body physics. But if I want to summarize, I would say on the left-hand side, this is the ultimate dream of a fully programmable quantum device, small number of qubits, you need error correction. The remarkable thing about this sort of these kind of condensed matter-like systems is that it's scaled to a very large number of particles. Of course, we can realize in the lab only a very restricted class of Hamiltonians, but they come with very high fidelities. So at that point, you might sort of think, can we somehow marry these things? Is there something in between this ultimate control versus sort of partial control that we have? And one of the recent developments along these lines is what we call a programmable analog quantum simulator. The word programmable is over here, and we'll see actually going to work in a few minutes from now when I show you results, what we can do with that. One example is the trapped ions that we have over here. It's a little bit washed out, not sure why. And here the Rydberg tweezer array. What you do with the Rydberg tweezer array is this, that you take an atom in the ground state, and you can actually trap it, very similar to what we do with the tweezer in biology, as a single atom, and we can store many of them in free space. And so what you do is that you randomly load all of these tweezers, and if you see that there's an atom inside, you move it over here, the next with an atom here, over here. So it's really building up quantum systems sort of one by one. But if you look at the distance between the tweezer arrays, it's typically of the order of a few micrometer. You might wonder, how can we make interactions? Well, again, we wrote a paper on the theory side about 15 or 20 years ago, proposing that we should excite these atoms up to the Rydberg states, and then we can turn on dipolar or maybe van der Waals interactions between these huge dipole moments that we have in the Rydberg state. And if you go through all of the math, you'll find that you get certain spin Hamiltonians out here having long-range interactions with all of these controllable parameters. At that point, if you want to do quantum simulation of this model, there's a lot of interesting physics. With Misha Lukin, we published recently a paper seeing, for example, a quantum version of the Kibble-Surek mechanism using all of these controls here and so on. And we have a similar situation with the ions here. We have a set of ions, storing the qubits here, and they realize, for example, if you integrate out the phonons that are spin-dependent, eventually this becomes a long-range Ising model that we have over here. You can see there's a long-range parameter down here. You can make it infinite range, you can make it short range, so there's a lot of control in that. So if you're happy to do this quantum simulation, but there's a lot of interesting physics, one can do that. But we should also note over here that we can add, for example, things like single-site control. The distance between the ions over here for the Rydbergs is of the order of micrometer. This is where you can focus down the laser. So you might actually combine these Ising possibilities that you have here, which are entangling, highly entangling, with a single qubit control that we have over here. And then you might simply say, well, what kind of models can we do? Now we can sort of go back what we do in quantum computing and take these elements over here, this Ising interaction together with the local control in order to build now up quantum circuits. And I will afterwards give you examples for that, doing, for example, variational quantum simulation, where we can build variational wave functions, where we entangle, have single site operations, introducing variational parameters over here. And I will give you examples then actually afterwards for these kind of ideas. This is a very recent development, and I think that this Rydberg tweezer array is a very exciting thing, and you will see much more coming out in a few years. And we believe that we can scale these things up to about a few hundred qubits. Then it will stop, because then we got some fundamental decoherence coming in, but a few hundred, I guess, is sort of a reasonable in this context. I will now in the following illustrate some of these ideas and how we do this thing in the lab eventually. So I'm a theorist, a doctor, experimentalist, but sort of what I would like to tell you in the following is that at the moment sort of our ultimate dream is becoming true. 25 years ago, we proposed many of these devices, having ideas how this could be built, like Eintrap quantum computer, these Rydberg's, Hubbard models, and all of that. And it's very interesting now for me to see that, in particular, with the situation that we have in, for example, Innsbruck with the trapped ions, Rainer Platz group, that we as theorists have actually access to these devices, and we can really program now. So the ultimate, promise that we had is this, that this would be programmable quantum devices where these theorists might be solving some problems. And this is becoming true actually right now. And I would like to show you afterwards the quite interesting situation that we have in our labs at the University of Innsbruck and our Academy Institute. I would like to focus here on one example because it's so simple, but at the same time, it's what we actually did very recently. And this is the Lattice Schwinger model. This tries to relate now sort of to the community here that's interested in quantum field theory. And all of you know that the Schwinger model is a form of one-dimensional quantum electrodynamics for mass equal to 0 in the continuum. You can solve it exactly. There's some triviality in the model, but it's not completely trivial. And this makes it, of course, an ideal framework for trying these things out and trying to demonstrate these quantum simulations. So what is actually behind it? Well, if you make a lattice model, you got here lattice sites over here. You got fermionic matter fields, electrons, the anti-electrons here, and you got the electromagnetic field here, the boson. These are the lattice sites here indicating where the fermions in our matter field sit. This is the electromagnetic field sitting on the link. So this is a proper gauge theory that we have here, lattice gauge theory. And we introduce, of course, what we call staggered fermions, where the even and odd lattice sites are such that this is where the electrons and also the anti-electrons, in our case here, sit, and then we write down the model. And there's a very clear-cut old story, behind these things of how to write down the corresponding Hamiltonians. This is indicating one particular configuration. For example, here, you would like to have a configuration where there's a vacuum over here, here's one particle, here's the other one, and so on. These are configurations. Our state will be a superposition of all of them. But of course, in quantum electrodynamics, we have the Gauss law. And this, of course, is the gauge invariance. This is the local conservation law that we have in the lattice gauge theory. And the simple thing in our case in 1D, and this makes the Schwinger model sort of so trivial to some extent, is that if I give you a certain fermion configuration over here, it gives one-to-one the corresponding electric field. So we can integrate out the quantum degree of freedom corresponding to the electromagnetic field. And this will be the toy model now in the following that we would like to use in order to demonstrate some of these quantum simulations in the way that I will explain to you. Here's again the electric fields that you would sort of build up, and as I said, they can be eliminated. And at the end, I will show you results for actually trapped ions. These are fermions over here. In 1D, we can just do actually a Jordan-Wigner transformation, mapping these various configurations onto spins and so on. This is simply what we call the Kogut-Susskind encoding. I mean, story that's principle very old, but we just sort of recycle it over here. So at the end of the day, if I call L the electromagnetic field, the electric field, there's no magnetic field because it's just in 1D. We have here the Gauss law that we can sort of integrate, and you can see that these electric field configurations over here, they are related to the charges which are sitting here, and this is the right-hand side, including the corresponding background, and we can then write the proper Hamiltonian that I'm not going to explain much more. Here's the coupling to the gauge field, and then over here, this would be the mass term of your electrons that you have, and this would be the electric field squared. So L squared is simply the electric field squared. So in that case, we can actually eliminate the electric field, and we come up with a model. Don't even try to look at it. It's a very ugly spin model, okay? So the question that I will now ask is this. Let's take this model and put it on our quantum machines and see if we can actually do quench dynamics or if we can calculate ground states. Can we see phase transitions and all of these things computed now on the quantum device at the moment for a very small number. I mentioned before that we can build analog simulators, directly by mapping our models onto real physical systems like Hubbard models. This has very strange long-range interactions that are peculiar to these eliminated gauge fields over here. So if you multiply these things out, on one hand, they're simple, but they have very strange long-range interactions over here with a very unusual kind of coupling. So there's no hope for doing that. I want to emphasize that in the following, symmetries will be very important. I will show you some results for variational quantum simulations where we imprint these symmetries in the quantum circuits that we are generating, but you will see this now in a minute. I would like to tell you now two stories in this context. One, which is now a few years old, and this was the story of the digital quantum simulation where my colleague Rainer Blatt has an ion-trap quantum computer, now about 10 qubits. A few years ago it was 4, and this is the results I want to show you. And then you can take a quantum system, a certain Hamiltonian, and you can look at the corresponding time evolution from over there. And the way how digital quantum simulation works is like this. Well, let me illustrate it down here. If you got some time evolution operator and say H is your many-body Hamiltonian, which I write down here just for 2 particles as a spin model. Here's the interaction. Here's a corresponding magnetic field term. You can see that they will not commute in general. What you do then is that the time evolution operator can be trotterized in small time steps, and this trotterization then amounts to taking these 2 parts and writing them on separate exponentials here. So this means that I can look at the time evolution, the quench dynamics of my system, essentially as something where I can put gates locally on my qubits, maybe certain kind of entangling gates, which at the end sort of mimic the time evolution from this Hamiltonian. So this is like an Euler kind of a stepwise propagation of your many-body wave function that we program here in terms of quantum gates. Well, this was the result. So we want to look at, say, Schwinger pair production. It was done on an ion-trap quantum computer in this very minimal configuration of only 4 ions. We were able to do 4 trotter steps, but the thing that you should be impressed about is this, that behind the trotter steps over here, doing all of these quantum gates, there were actually 220 quantum gates that were applied without any error correction, before the whole system fell apart. So I think that that's quite amazing. The 4 qubits and 4 trotter steps are really absolutely minimal, and you can do them on your laptop, of course, right away. But to do in the lab 220 quantum gates and then to really demonstrate and the pair production over here, and this is comparison theory with the experiment, I think it's actually quite impressive. In the meantime, we can actually do these things for larger, but never mind at the moment. Let me now change my story and sort of switch over. You can see now down here the word 20 qubits, and actually in the lab right now, since about a week, there's actually 50 qubits. But I give you now a somewhat different story because I would like to talk now, instead of quench dynamics, how we can simulate on our quantum devices. And the keyword now here is programmable quantum simulator. I'm not talking about a universal quantum machine, but about this sort of partially programmable machine, these programmable quantum simulators, in this case of the trapped ions. And I will show you afterwards that we would like to do variational quantum simulation for ground states. And the non-trivial part in the whole story, well, the whole thing is actually non-trivial, as we'll see at the end. The really part that we get excited about is the fact that this will be self-verifying quantum simulation. So our computer will tell us the energy of the ground state, and it will also tell us by measurement on the quantum device what the corresponding variance is. So it gives us the value, including the error bar. Okay, so this is the not to do variational. You know that you got an upper bound. This is really also producing the error bar, and this was the exciting thing about it. And this paper came out this year, a few months ago. So what do we do? Let me now show you, and you may find this entertaining in this context, this sort of quantum computing or programming environment. We call it the Innsbruck Quantum Cloud here. This is the Google map that you have from our campus. It's a technical campus of the University of Innsbruck. This is where the university labs are. This is the academy. Part is actually part over here, including labs also. University labs are over here. And if you take these 2 buildings, we as theorists sit in this academy building here. What theorists normally do is this, that they have their little computers and they play their game, maybe solving some many-body problems, simulating this and this. And I want to mention here Christian Kochel and also Rick van Bijnen as the PhD student and postdoc mainly involved in this context. But the interesting part is that down here in the basement, there is a 20 qubit, and I said now since 1 week or 2 weeks, a 50 qubit machine as a trapped ion analog quantum simulator that can be programmed. So before I talked about programmable, this is the machine that realizes, for example, Ising interactions, but you can also add single particle rotations here to this whole story. Yeah? And then we have a quantum computer over here with a much smaller number of qubits. So you can see this is now 50, and this is still maybe 10 or something like that. So you can see the difference between these machines. So normally what theorists do is this, they write maybe some computer code to simulate some many-body problem. But in our codes, there's a flag, and the flag is called, flag quantum processing unit false, and then it runs on a classical computer and simulates that. This is what all theorists are doing at the moment. But the interesting part is that we can also access with the same code our quantum machines. There's all of these interfaces, of course. At the end, all of this has to be translated into laser pulses, into readouts, and all of that. So there's a whole quantum compiler, several layers. But at the end of the story, what it means is this, that we as theorists can run our code, or part of our code, on these quantum machines by programming them directly. We get some output back. And it is very interesting. I wrote down here quantum feedback loop. We can do these things 10 to the 5 times, and then do, for example, variational quantum simulations by calling a quantum processor now very often, and then therefore, producing some results. This is how it works. I mean, we have here hybrid classical quantum algorithms. We have here classical computers, some quantum coprocessor, let's call it, that optimizes or finds out a certain function psi of data over here that we build with our quantum circuits that we have available. And the way that we do it is just a textbook example of variational physics. We define cost functions, say the expectation of a Hamiltonian, but it could also be other things like, might be interesting in squeezing. Recently with Junier, we wrote a paper about how to optimize, for example, squeezing for use in, say, quantum metrology. You have a certain cost function. You'd like to optimize this with certain variational parameters on the classical machine. The circuit over here is parameterized in terms of the theta, and we evaluate these things on the quantum machine efficiently. So quantum mechanics sort of gives us here the expectation values, and in terms of these measurements that eventually come back. And notice that this wave function that we have at the end, it is actually stored in quantum memory. So it's ready to be used as a quantum wave function, as a true entangled state that you generated on your quantum device, maybe for some other tasks, say like quantum metrology, as I mentioned. Features is that we perform optimization on an actual physical quantum device, which is the ion trap over here. It's a multi-qubit quantum processor. It's not a quantum computer, but programmable machine, not universal, but pretty scalable. And we want to see, of course, entanglement over here beyond classical, and I'll talk about entanglement quantification then afterwards. Well, and the cost function really depends on the problem that you have over here. Let me now become a little bit more concrete. Suppose that I take now the Schwinger model that I talked about it before, and I just wrote it in a very schematic form, and it's this ugly spin model that we don't really want to look at. And you can now take this thing over here, and instead of programming trotterized quantum evolution, what we can do now is this, that we can try these variational ideas by taking ions, and we have building blocks of gates available, like these, I don't know, Ising interactions here as one example, local rotations, and then you can build up a family of wave functions over here that are parameterized. Afterwards, we will have actually 15 variational parameters that we will optimize classically in a global sense, defining variation parameters, and this defines then the depth of your quantum circuits, how many of these unitaries you do over here. And as I said, we can do eventually something like maybe 6 layers. This is where we stopped. And the main reason is that the classical computer doing the optimization is running out of power. Our quantum machine could actually do much more in this context, but we have ideas how to use that. So this at the end is then, how it works. Suppose that you have a certain target Hamiltonian, can be anything that you want. In our case, it's the Schwinger model. And then we are building up here these building blocks, programmable quantum simulation, variational wave functions at the end that sit in quantum memory. And using these wave functions here that are parameterized in terms of this data, we do then measurements over here that measure the relevant correlation function. If we want to work out the cost function down here, you can see we need the expectation values of these Pauli matrices in a given basis, X, Y, Z. We have 2 body terms, maybe 3 body terms, and so on. And you have to measure all of these correlation functions, and this is what we do. And usually, in order to get one of these correlation functions, we have to do about 30 runs. This would be the shot noise in the story. So it's very important to talk about noise in this whole context, and measurement noise and projection noise that we get, and so on and so on. But at the end of the day, we can get some results. And I just want to show you one highlight over here, which is an optimization trajectory for the Schwinger ground state. We can do this for 20 ions. Actually, the plot that I show you is for 8 ions, because here we have the self-verification. We can really see as a function of these iterations that we do classical quantum, how the energy is sort of going down. We have certain models here predicting based on the simulation results, what the expected value is for this energy. And at the end of the day, we sort of simply declare here the optimal value that we got from global optimization algorithm. This is sort of like applying machine learning artificial intelligence, if you want, sort of to optimize this whole thing over here for this variational ground state. At the end of the day, we got here wave function. And the interesting part is now, if you take this wave function, it's actually very easy to reproduce. Once you have the 15 variational parameters, you just reproduce it as a circuit. And then we can not only compute the expectation value of h in our quantum machine, but also say h squared. And all of you know that the variance of a Hamiltonian in an eigenstate, of course, is equal to 0. And we use this as a test of the error. And you can see that this error sort of decreases over here, becoming less than the distance to the first excited state. So we're really sure that we got in the specific magnetization sector that we're in here, which is the vacuum sector. We really got the ground state, with an error bar, which is indicated over here. And I emphasize that, of course, we do a lot of classical simulations testing all of that. And this is what we expect, this is what we measure, this is what we expect classically over here, these crosses. There's really fantastic agreement. You can see this quantum machine of 20 qubits at the end really does what it's supposed to do. It does coherent quantum circuits that we can program, and it's quite amazing that, that this works today in the lab. And notice that all of these data that we call experimental are really only experimental. There's no theory that we put in. Actually, if you ask, what's the overlap of the final wave function that we get over here, variational, with the exact ground state that we can compute, of course, for these very small systems, in the Hilbert space of, say, 2 to the power 20, which is huge, it's about 85%. So many body wave function in this huge Hilbert space, 85%, I think is a pretty good number. This is an indication, and this is typically about 6 circuits. What's kind of interesting here is this, that we have here, we can also, this can be a playing ground. We ask ourselves, can we see quantum phase transitions with that? And we can do something here that I guess experimentalists would find very hard to do. We can take the mass parameter in our model and have it positive or negative. Of course, if it's positive, this thing over here would be the normal vacuum out here for very large mass. If I take the mass negative, you would get many electron-positron pairs that you generate. So there's a quantum phase transition between them. This is the theory curve. This is the experimental results. So we see indeed a quantum phase transition. What's maybe more interesting, and this now takes me to the next part of my talk over here, is the fact we can also measure entanglement over here. I started out by talking about entanglement, so you might ask, how do we measure this entanglement? I'll talk about Renyi entropies in the following, where we have a system over here where the total state is a pure state, or should be a pure state. We can actually check for that. We take a subsystem, there's a reduced density matrix, and the purity over here would be the second order Renyi entropy. And if you take this Renyi entropy, that I will afterwards show you how we measure that, then we get this thing over here. You can see indeed the entanglement, it's very peaked at the quantum phase transition point over here, as you expect. And you have to take a sufficient number of circuit depth in order to capture this entanglement, but you can systematically improve that. And of course, we can also measure the corresponding errors that are associated with all of that. So all of this is running on the quantum devices, and it took us about almost 2 years to get this thing done. And it was really us theorists programming these devices literally from our desks but of course, experimentalists should really get the credit for providing us with these incredible quantum machines that they built in the lab. So let me now switch over to telling you a little bit more about this Renyi entanglement entropy, because every talk on quantum simulation and quantum computing starts out with the word entanglement, and very often then people forget about this afterwards. We were asking ourselves, how can we measure that? And I want to tell you just one paper that appeared this year, probing Renyi entanglement entropy via randomized measurement. We have sort of developed new tools that I find very interesting, actually, theoretically. And the very recent paper we put on the archive was on cross-platform verification. So this is under review at the moment. We also have something on scrambling out of time order correlation function that we can do. We have some results for these things, but my talk will be too short to talk about these things. Yeah, this would be verification of quantum machine. I have a few slides on that, and I think that this will become very interesting when we compare, does a quantum simulator in Innsbruck, do the same thing as the one in Maryland, or maybe on a completely different platform. And so these are the kind of questions we are asking here. So we are back to measuring entanglement. How do we do that? Well, let me give you sort of what the key ideas are and what we want to do and how we then approach it. Well, I said before that suppose that this is a pure state, so your density operator would be something like that, and you bipartition the system into A and B. This is the reduced density operator. This is Renyi entropy for 2, the purity of the subsystem. It's a measure of entanglement. This is a pure state. Okay? How can we measure these things in the lab? Well, the first remark I have to make is that you notice this is a nonlinear functional. What we always know how to measure in the lab, of course, is expectation values. They are linear in the density matrix. So how do we get the rho squared in our context? Well, we have to play certain tricks, and well, one of them, of course, would be that if I'm able to do what we call a complete tomography, on the system, where we really make many measurements of the system, determining the complete quantum state, then we would be able to calculate, what this thing is, just on our classical computer. But this is very, very expensive. Experimentalists are able to do these things for maybe 8 qubits, but if you want to do more, then it stops. And we'll afterwards show you what we can do is actually a much larger number. And very often we don't know how to do these protocols. Okay. One answer to this story is something that we came up with some time ago, based also on some earlier papers, is you can measure these Renyi entropies if you got 2 copies of your quantum systems. And experimentalists very often are able to do that. What you have to do is this. Notice that if I got 2 copies of a quantum system, we have rho tensor rho in this Hilbert space, which is the one of these 2 chains that we have over here. So we have to convert the rho tensor rho into something which is the rho square, and in order to do that, we have to apply a swap operator, as we call it. It's written down here in terms of basis states that converts the tensor product into the rho squared. And then you can see at that point, this purity over here becomes the expectation value of a swap operator. You might ask yourself, how do you then implement the swap operator? Well, we came up with tricks how to do that. And indeed, for example, Markus Greiner, a rather remarkable experiment, has taken these ideas now. And you can see here 1 copy. Here's a 2nd copy over here. There will be certain beam splitter operations between that, and I'm not going to explain. He was able to do that. Okay. And so I'm not going to tell you more about these results over here, but sort of come back to the story that when I talked to my colleague Rainer Blatt, here's a single ion trap there, just 1 chain of ions. If I ask him to make 2 copies, he will smile and tell me that I should come back maybe in 10 years or so. So the question is, how can we, with a single system, obtain the same result? And the answer is actually a very simple one. Instead of a single system, why don't we sort of make a virtual copy? So it's kind of a replica trick that we implement here in the lab. And you will see afterwards what I mean by virtual copy here. You might say, well, quantum mechanics doesn't allow to make copies. We're not making copies, we're making virtual copies. And there's nothing about virtual copies being illegal, as we'll see now in 1 second over here. And the idea will be that we will perform randomized measurements. And you will afterwards see that these randomized measurements, by looking at cross correlations between fluctuations in these measurements, we are able to extract these quantities. So sort of in our case, the signal is in the noise. Very often in condensed matter physics, you also have that, and that's what we do over here. So what's the basic idea? Well, we have here statistical correlations in randomized measurement in the following sense. Imagine that we got a spin chain over here, and we have here a reduced density operator, and we apply here a random unitary. For the moment, this is a unitary to the 3 qubits. I will afterwards show you a protocol that works by only having unitaries on the single qubits that experimentalists prefer very much over the protocol that I'm outlining over here. Suppose that I'm applying this scrambling over here, this unitary, this randomized thing, then I'm doing a measurement in my standard basis. I get certain probabilities out that, of course, will depend on the U for the given quantum state that I had at the very beginning. If I now take the average of these probabilities over all the unitaries, of course, at that point, if I've done a good job in randomizing, these probabilities will be completely flat. But if I look at the probability square and then I average, then you can see magically here, this trace of rho squared, this Renyi entropy appears over here. And actually, the reason why it appears is very simple. We call this thing 2 design in the quantum information. If I write down this probability squared, then average, you can see when I square the probability, I can write it like in an extended Hilbert space. This is the first copy, this is the second copy, by just writing the probability on the single trace of 2 quantum systems. This is my virtual copy if you want to. And now if I sort of proceed, well, these random unitaries that we have over here, they have certain correlation functions, like there will be contractions, say the first with the second over here, this one over here, but also cross correlation that cross correlate the first copy with the second copy that we have over here. And this is the one that gives rise to the swap operator. So we have in principle protocols. If we are able to do randomized, we randomize our wave function, measure probabilities, square them, and then we average, we get our results out from over there. The question is, of course, what's the effort? How many measurements, how many random unitaries we have to do, but you will see afterwards that this works quite well. So one answer to this whole story then would be, can we apply a random unitary? When we went to the experimentalists, we had very concrete proposals how to do these random unitaries, but they were quite unhappy and said that we should again come back and only in 3 years with these kind of things. So we had to come up with something easier. And this was what they can do very easily, namely to do single qubit rotations over here. So this is no longer the circular unitary ensemble on the sub-Hilbert space that you're interested in, but this is sort of single qubit random rotations, by making random rotations of each of these qubits. And the answer was that we could derive a formula where we look at cross correlations between different measurements, with different measurement outcomes that contain these things. And here's the formula. I'm not sure I should go over this in details. Here you can see your probabilities. There's a Hamming distance between these configurations over here. And at the end, it was the average of these quantities that gave us trace of rho squared. This is, you can sort of see now, a randomized measurement at work here to extract very interesting quantum correlations that are usually very hard to measure in say, condensed matter systems. Well, we take a certain time evolution, quench dynamics. We take our favorite, say, Hamiltonian as a spin model that we can realize easily with trapped ions. And now we can measure, this trace of rho square for increasing system sizes, until we go to the whole system. So at the very beginning of the quench, this is the purity. It's supposed to be 1 over here, but measurement probabilities, have some errors. So we go down here to this value, which is 7.6 for, in this case, 10 ions. We can also do it for 20, actually. And then if I now proceed with my time evolution down here, and if I plot the same thing then also here for the Renyi entropy, you can see the total state basically remains pure over the total time evolution. But if I bipartition the system, say here in the middle, I got these Renyi entropies that peak over here, and that's exactly what you would expect from entanglement in this one-dimensional chain over here. But you can see that we know how to measure these things now, and I think that's it's kind of great to have these quantities accessible. We can also look at all of the subpartitions, but that's a detail. So let me, one more, I'm already in my cutoff time, or? Okay, so I have a few more slides on these things here. I just want to tell you that the same kind of ideas, and this is something that we put on the archive actually recently, also works for cross-platform verification. That's a very important problem. All of these different groups and companies are now building quantum devices. You would like to ask yourself, do they produce the same result, maybe even in the regime that is not accessible, where we can actually test them by classical simulations? So you have maybe one quantum device over here, one over here, and you ask the experimentalists to prepare in the quantum machine 1 and 2 the same wave function. And of course, if it's the same wave function, they can do these things on different platforms over here. You might also include theory in this whole thing, and then you sort of know the quantum state according to a theoretical model. Can we make these comparisons on the level of the wave function? So what do we mean now by cross-platform verification? The fidelities we're interested in is say, just the overlap of these two wave functions, but one may be in Innsbruck and the other one in Maryland, say. What in principle you have to do is teleport our wave function over, and then we contract the wave function. We have to wait for some time for this thing to happen. So we would like to find some classical protocols, which at the end are always exponentially expensive, but they are much less expensive than, say, doing tomography. This is where this whole procedure comes in, and I want to show now some first results along these lines here. So in the case we're interested in, we take then a subsystem over here, look at the overlap of the two density matrices, and we would like to find a classical protocol doing that. And the answer is this, that, well, I just showed you before how we can measure Renyi entropies. This was the story over here for a single chain. Suppose that you do the same thing on the other side, for your second platform. Well, at that point, you measure the purity here and here. It's a story I told you before. But we can also look at the, if you use the same random unitaries here and here, at the cross correlation of these probabilities of these two machines. And this gives you these overlaps that we have over here. So we are able to extract fidelity of quantum overlaps, in our wave functions here. And this is only a classical link, and it's sort of more efficient than homography. Here's what we did so far. In Innsbruck, there's only one quantum simulator where we can do that, so we don't have a second machine. We simply said, well, let's take theory as the second part. So we have theory based on certain Hamiltonians, experiments over here. These are sort of first results that were extracted actually from old data, and we found that there was some measurement errors in here. You can see this would be the model to compare with. This has a little bit decoherence on the theory side built in. This is for increasing number of subsystems looking at the overlap. So what you can see over here is data for a 10-ion many-body wave function after a quench. This thing is seriously entangled, you know. And then you look at the overlap. Does your theory wave function on the level of 10 particles, the complete entangled state, in a product, you know, with the one that you have on your quantum machine, and you can see the results about maybe 75% or so, and it doesn't really change as a function of time. And the reason why this is not equal to 1 over here, well, first of all, maybe theory doesn't capture everything completely, but on the other hand, of course, there will also be certain imperfections, in particular in the context of measurement. It turned out that the implementation of these unitaries, they were off by a certain angle of 3%, and this could explain this result. So we really want to go back, but our ultimate dream is this, that we ask maybe Chris Monroe in Maryland to do a similar experiment, and then we would like to compare the 2 quantum machines in Innsbruck and the one in Maryland on the level of these wave functions. And this brings me to the end of my talk here. I gave you sort of a tour of recent developments on this, let's call it atomic intermediate scale. You know, this is sort of going up to 50 or whatever, maybe 100, including verification. I told you about quantum simulators. There's a whole story about quantum sensors. So with Junier, Anna Maria, Adam Kaufman, we put a paper on the archive recently that's in print now in PRL. Where we are using variational techniques to optimize, for example, squeezing for quantum sensors with a given physical resource that you have. And it's very similar to over here, where you get squeezing as a function of time to do that. I don't have, it turns out, I guess I don't have time to do this now here. I find it very exciting to think of these variational ideas in higher dimensions. 2D, I would like to include fermions, Fermi-Hubbard models. We have very specific ideas how to do variational quantum simulation with experimental devices in an efficient way with fermions in higher dimensions. To make this thing programmable, I think that this is extremely promising. I could tell you a little bit about it, what we're trying to do right now. And then, of course, we have this whole story of randomized measurement that turned out to be, well, I could tell you about out of order time correlation functions, scrambling and all of that. We have measurement results for these with these systems over here based on these randomized measurements. So this idea of randomized measurements that we've been working on over the last few years turned out to be kind of a gold mine and a completely new direction how in atomic quantum simulators we can extract quantities that are normally not accessible in standard experiments. Usually people look at some low order correlation function. We can really look at quantities that are very difficult to access, like, say, topological invariance. You get a topological many-body system. You can measure topological invariance in these kind of things, test certain symmetries, and so on and so on. And it's just part of this whole toolbox over here. Well, and with this, I would like to stop over here and had a few more slides on this quantum sensing, but in view of time, I think I've run out of time. Yeah, thank you very much.
Thank you very much for this really exciting subject which you exposed to us. Are there questions? Please.
Peter, for randomization, how do you know a priori how big a randomization set you make?
Okay, that's very good. This is about, I had some slides about these things, how many measurements does it take and what's the scaling with the number of measurements, also the number of unitaries that we have. So, I think I even have some slides over here. This is the part of the quantum sensor that I didn't show here, some results on that. So these are results. Basically, we have a scaling of this thing that goes like 1 over the number of measurements and then square root of the number of unitaries. Square root of the number of unitaries, you can sort of understand in the sense that this is simply central limit theorem. The reason why we got number of measurements over here is related to the fact that we take the probability squared, okay? And so 1 over squared number times another one gives 1 over n. And this very simple argument seems to fit extremely well with the scaling that we observe in numerical experiments that we can do up to, I don't know, 10 or whatever. In this case, it was actually subsystems of 8 over here, qubits, and this tells you the scaling. And the question is, of course, I mean, what does it mean in practice? So in practice, something like, I don't know, maybe 150 unitaries, then combined with the fact that you have here a few hundred measurements, sort of, is roughly the budget that you need in this context. Yeah.
Please.
Microphone.
Thank you. Fascinating talk. There was just one step, maybe I misunderstood something. You said at some point that for measuring the Renyi entropy, you could go from these random unitaries, which in effect sort of make swap gates. And then afterwards, you said you can have single qubit rotations only.
Okay, yeah.
How is that possible?
Well, the answer is read our papers. Okay.
Is it easy to see that?
I think it's not very easy to see. One really is to go to these calculations, and we wrote very long papers that go over many pages deriving these kind of things, and there's various ways of deriving these results. So if you ask me, is there a simple answer? I would say not really. And so, sorry, but just read the paper.
No, I'm happy you said that because I thought I'd missed something that was very obvious.
That's not really intuitively obvious here.
Okay, thank you.
Last question.
Hi, Peter. What would, if in the longer term, what new physics could you discover with these quantum simulators?
What new physics we can discover? So I would say, first of all, it would be, if I take this paradigmatic model of, say, the repulsive fermionic Hubbard model in 2D, this is one example where theorists so far have not been able to reliably compute the phase diagram. And I think that it is very clear, provided that temperatures can be achieved, that these quantum simulators will provide the corresponding phase diagram, but also there may be much more insight in the sense that all of these higher order correlations functions that are typically not accessible in some of these experiments would become visible over here. The other part is this, that if you look at the variational quantum simulation that I described over here, of course, there's a lot of ideas like this in the context of quantum chemistry. We are doing lattice models in our context. You might simply ask, can we use our devices by sort of programming them in a way that would allow us to explore, for example, phase diagrams of certain models that you cannot physically realize in the lab, but you can approximate something which is close, but then sort of doing the variational by writing down a target Hamiltonian versus the resource Hamiltonian. One is able to compute then here quantities of phase diagrams and entanglement properties and all of these things for these quantum systems that maybe eventually, we hope very much, will be not available on our classical computers in order to actually simulate these things. Yeah? And I would really also emphasize, one major advantage that I see here, if you just take our variational example here, at the end of this procedure, if I take quantum sensing as an example, and I really love this example, and it was sort of inspired after being a chiller for 1 month with June and then Adam and Anna Maria. If you would like to have squeezing in a quantum device, say in an optical clock, it would help you based on entanglement. Nobody has used it so far. It's not at the point where people have been able to do that. But I sort of ask you the question. You would say, I would like to have squeezing in my atomic clock. And then you would say, what entangling features you have available in terms of interactions in your physical device? And you tell me this and that. Okay, and then I said, what would you like to optimize? And you tell me squeezing. Okay, so we would write down the cost function in terms of squeezing. We would sort of, optimize these variational parameters within the set that we can do. At the end of the day, for the given resources, you have the best variational wave function sitting there, and you can very easily regenerate this wave function, of course, which now sits in quantum memory, sort of ready for a task like, say, quantum sensing. So we should see these things much broader than only quantum simulation. It's also quantum sensing that comes in, and we would like not to say, well, suppose that you got the universal quantum computer, then I can program whatever you want. We have finite resources, we have finite numbers of particles over here, and we have finite fidelities, all of that. Given that, sort of like this variation we talk about here would be one very nice example where we can say, what can we do in the lab right now that uses this kind of things with the given resources? But really go also beyond quantum simulation. So quantum simulation, for me, one example.
Thank you very much, Peter. I think we have to stop here in view of the delay which we already have, but we will have a discussion session where we can come back to quantum simulations and this quantum system Peter talks about. The next speaker of today is Renate Loll. Let's thank our speaker again. Next speaker now is Renate Loll, who will talk about quantum gravity made simple but not too simple.
Here. No. It's this one. Doesn't she need to connect her computer? She has to talk. She has to talk on your computer. Is that remote disk? I'm not sure. It sees it. It doesn't see it. No. It's trying to inject it. It's a QFC. It's the top. Thank you. And is it the pointer for these? Ah, yeah. Okay. And for these, so? Oh, or is it a normal? No, I want the normal one. Yes, I want the normal. For the light? Yes. Only for the light? Yes, only for the light. But this I need for changing. I see, my God.
5 minutes warning after 35 minutes. So if you then go on for 5 minutes, then 35 minutes.
So anyway, okay, we stop.
Then you start.
Okay, so we stop at 5:02 in principle with everything. Okay. Okay, with apologies for the delay, the various delays. I want to start also by thanking the organizers for pursuing the honorable task of bringing together different parts of the community. And my task for the next 45 minutes will be to instill some idea in you of what we are trying to do in quantum gravity. So it's about quantum gravity made simple, but hopefully not too simple. So there's still interesting things we can say. So here's a preview of my talk. So the context of what I'll be talking about is to try and understand quantum gravity beyond perturbation theory. And I've been following a specific research program, that of causal dynamical triangulations. You'll hear a little bit about in my talk, that addresses the problem. But of course, the issues are of a general nature, and I will spend quite a bit of time talking about those. So my main message is that if one takes the dynamical character of space-time into account in the full quantum theory, as one tries to do when one goes kind of non-perturbative, and that implies, by the way, the absence of any fixed background metric or structure one can refer to, even with completely standard tools, you get to quite extraordinary and surprising results. So following this, of course, it's a line of ongoing research. We've got some completely new insights into hopefully into the nature of quantum gravity. Of course, we are not there yet, so we cannot be sure without an appropriate phenomenology that we are on the right track, but it looks promising and interesting. So what I'll do, of course, I don't have too much time for all these things. I'll give you motivation and context. Of course, already yesterday, one of the speakers said, "Ooh, maybe this is all speculative physics." Of course, we are more serious than that, so I hope I'll try to address that point to some extent. So we are doing very concrete things with tools that should be to some extent familiar to you if you work on quantum field theory, if you work on statistical mechanics. And this is what this approach kind of embodies of CDT. So it's simple, but hopefully not too simple. So there are some crucial things which this approach seems to get it right, at least that have enabled us to make a progress. So one is how to deal with coordinate invariance of the theory, so it's kind of the gauge invariance of that theory in general, and the importance of a causal structure that seems to be an ingredient one has to add in kind of the ingredients one chooses a priori when one starts formulating the theory in order to get something interesting out. So there are two aspects of interesting results. So true quantum signatures, so true kind of quantum effects of this formulation. And on the other hand, linking back to the classical theory, so the classical limit, and that also has to do with notions of emergence of various features. So we'll see a rather concrete way in which this is realized in this approach. Okay, so we live, I would claim, in the century of gravity, and you have already heard quite a bit about gravity yesterday. So gravity is interesting because it's kind of the oldest theory of interactions we know, and you certainly as Pisanians are well aware of that, letting things drop from towers. Of course, it's a very real force, but in a way, it's the least understood of the four interactions. Namely, its quantum regime is only very incompletely understood. So really, to link up, in some sense, to this enormous wealth that seems to be opening up in terms of astrophysical observations, of course, gravitational waves now, the new window that has opened up. There is all the more an urge kind of to complete gravity theory at this end, although it is at very, very short distances and at very, very high energies. So, and we want to do this, hopefully in a way that leads us to a reasonably unique theory. So one way of going about that is to try and start from rather, that's my approach, rather conservatively, kind of get away with as little as possible, with as little, additional assumptions, initial assumptions, and also try and aim for a small number of free parameters. So, kind of things one still has to tune. So, in doing this, I will tackle quantum gravity in a very direct way. I will work more or less with the degrees of freedom of the classical theory, but in a very non-perturbative regime, so the so-called Planck scale. And this is to be contrasted to ideas that are followed from people who are rooted in ideas of superstring theory, which rely these days a lot of the existence of dualities or dictionaries between gauge and gravity theory. So I'm not going to rely on this at all. I'm jumping in at the deep end and trying to understand what one can say in such an approach. Now, let me remind you of the beauty of classical gravity. The way it is often phrased is that this is not a theory on space-time, but it's a theory of space-time. So it's not stuff, you put onto a priori fixed background space-time, but really space-time itself becomes dynamical. And of course, the way this is captured in general relativity is in terms of its curvature properties. Yeah? So here we have, a heavy object deforming a space-time, so making it curve. And here's, of course, one of these beautiful pictures that has now become much more real and directly observed, that of two heavy objects spiraling into each other and emitting a gravitational and a time-dependent signal, gravitational wave signal. Now, from the point of view of the quantum theory, you could say, okay, classically, this is a theory of space-time, and like curvature is a very essential quantity. So does that mean when I now do non-perturbative quantum gravity, kind of the same logic should apply? So everything should be, talking about maybe quantum curvature. Now, there's a good reason, while you will rarely have heard anyone talking about quantum gravity, talking about quantum curvature, and there are very good reasons for that. And we have only very recently, in this approach, made progress, however, although a priori it's not clear it should exist, in defining a notion of quantum curvature. I will not have any time to talk about this, but this kind of represents kind of the line of research where we stand, kind of the frontier of research, trying to capture a local, what is classically a local property of space-time in a quantum regime that is very, very far away from any smooth and nice classical properties and geometric properties. Okay, so to set the thing into context, yesterday especially we heard a lot of talk about things happening at various scales. So this is, of course, a logarithmic scale, and this, is the range of scale a theoretical or a physicist may be interested in. We have heard a lot about technology, for instance, to do extremely accurate time measurements, but they are somewhere here in the atomic scale. What I'm talking about, these are length scales in powers of 10. So here the very largest scale is that of the visible universe of about 10 to the 26 meters. Of course, you zoom in, and here is kind of atomic scale. These are kind of the smallest distances we can resolve in today's particle accelerators at the LHC. So this is 10 to the minus 19. That's the realm of constituents of atoms, quarks, gluons, and the like. But where the length scale, where we expect that quantum behavior of gravity and its interactions are important, is this extremely small scale of 10 to the minus 35 meters. Now, so this is kind of what I call the habitat of quantum gravity. Now, of course, what I'm interested in is really where does gravity play a role? So it's quite interesting, right? Because gravity is weak. We don't understand really why this is so, but gravity is very weak. So wherever on atomic scales, or subatomic scales, it basically plays no role because it cannot compete. It's just so enormously much weaker than those interactions. However, when we get to the very largest scale, because electromagnetic interactions, which are also long range, basically kind of cancel out, what we're left over with is gravity. So gravity wins at this end, and there's a good chance that if we go to these very, very short distances, again, gravity becomes the dominating effect in dictating kind of what becomes of space-time at these very shortest scales. Now, this raises many interesting questions, obviously. So a very crucial one is, well, I'm interested now in describing this quantum dynamics, but somehow, well, obviously I cannot perform direct measurements at that scale, but can I imagine that there is kind of some collective effect from these whatever wiggles at the shortest scales that leads in some way or other to, say, some astrophysical effect on large scales, which I may go out and try and measure and verify. So by imprint, I mean imprint in a wider sense, not simply on CMB as it's usually used, but kind of an observable effect. Can we come up with such a thing? Now, there are definitely questions that we would like quantum gravity to answer, so let me just highlight a few of them. Well, cosmologists are interested in the early universe, or the very early universe. So the way I phrased it, we are interested in the quantum behavior kind of in the even earlier universe. So that period of the universe, so we're going back in time where energies rose to the extent that the classical theory is no longer applicable. So there is then, whatever, a fraction of a millisecond where, with a quantum theory of gravity, I might be able to describe just that much more. Yeah, so that's one of the ambitions, obviously, of quantum gravity. So we are talking about the vicinity kind of the origin of our universe. Now, there are very, very interesting questions of a general nature that open up once space-time is no longer a fixed entity. So then you have to start asking yourself, properties of space-time that I conceive of as just being, God-given, just being there, well, you may start questioning them, because once space-time itself becomes dynamical, various of its properties may perhaps even no longer be present at the Planck scale. So a lot of speculation, so genuine speculation goes on, people saying, well, space and time, maybe they cease to exist in any sense of the word at the Planck scale. Maybe even very fundamental physical principles we follow everywhere else in physics can be thrown out or overboard. So things like causality, locality, unitarity, maybe they don't exist or don't make sense at the Planck scale, but maybe magically they emerge on somewhat larger scales. Now, for the most part, these are just very hand-waving ideas, because it is extremely difficult to put anything like that in practice or to make it work. So it's really the old emergence idea. I have a microscopic system with microscopic constituents, which may have very little even to do with what I recognize as geometry, but that display, when I kind of zoom out on a larger scale, kind of collective behavior, then that all of a sudden, oh, I see, general relativity re-emerging. So that's a very, very tough call to show that something like this happens. So another question, interesting question here, can we actually derive gravitational attraction? Why is gravity attractive? Why do we have Newton's law? Why does it look like that even before we start talking about Einstein gravity, general relativity? Can I derive this somehow from first principles quantum dynamics? We currently cannot. And then, of course, again, speculative ideas that relate to phenomenology. So if quantum spacetime, empty quantum spacetime, has some interesting microstructure, could that lead to some more macroscopic effects, like change dispersion relations of light that reaches us from very far away? So these are also ideas that people have entertained. And can we kind of use microscopic physics, again, to explain what we see macroscopically happening in our universe? For example, that on very large scales and at late times, it looks very much like a de Sitter universe. Or perhaps even, can we ascribe dark energy, now if it really exists, to some kind of microscopic, non-trivial structure of space-time at the Planck scale? Okay, so now let me zoom in a little bit of what I mean, or what we mean in gravity when we talk about going non-perturbative. Now, so there are various ways in which you can think about gravity. So the crucial dynamical variable that we use in the continuum is this g mu nu of x, right? So g mu nu is a Lorentzian space-time matrix that captures all curvature properties that your space might have. So this is a dynamical quantity that underlies general relativity. Now, classically, what always happens, so this is a little bit, these items go along in inverse order with this picture here. So what I'm doing, I'm zooming in on a piece of space-time, empty space-time. Now, what is true in the classical theory, of course, we know that space-time can be curved. However, when we go at just a little piece here, if we just zoom in far enough, it will always start appearing flat, so structureless from a gravitational point of view. So that's true for a classical spacetime, and that's also true for the way in which we describe classical spacetimes in general relativity. So that means if I go to sufficiently small scales, G mu nu will always look like the flat Minkowski metric. And that is, of course, what works extremely well when we do lab experiments, where I already said, if you study particle accelerators, forget about space-time curvature. It's mostly just completely irrelevant. Now, what we do, for example, to talk about weak gravitational fields, for example, gravitational waves far away from the source, as we observe them here on Earth, we look at linearized classical gravity. So where I can approximate G mu nu as the flat background, plus some kind of small space-time ripples of some H mu nu. So that was also already a similar formula we had on the slides yesterday, where these H's are very, very small entries compared to the eta mu nu. And of course, the ingenuity of people observing gravitational waves is measuring this, 10 to the minus, whatever it is, 22 deviations from things of order of magnitude 1. Now, perturbative quantum gravity kind of repeats the obvious perturbative ansatz at the level of the quantum theory. So I'm putting heads on things kind of to indicate now we're talking about quantum theory, everything are good operators, hopefully. So what one does here, one can do the same thing. You say, okay, let me assume, basically, let me consider a quantization of this linearized context. Let me assume gravitational fields are not too big. Anyway, the gravitational constant is a very small constant. Let me make a perturbative expansion. And let me just describe quantum gravity perturbatively as I do it for other quantum field theories. Unfortunately, as we have known since the 80s of last century, this leads to a non-renormalizable theory. That means it is not meaningful, so it has divergences that cannot be absorbed by a redefinition of coupling constants or of a finite number of coupling constants. So it doesn't really make sense to try and describe Planckian phenomena as we want to do perturbatively. So then one route that is open to us, so we are going, this is semi-classical, this is flat, here space-time is developing ripples, and then this is here, this artistic impression of what might happen to quantum spacetime on very short distances. You see some kind of spacetime foam, maybe topological excitations, what have you. So that's what people now start saying. Okay, a nice smooth G mu nu is probably not appropriate to use in that regime. But then what takes its place quantitatively? How do we build our models, our quantitative candidate series of quantum gravity? So what becomes of spacetime and the degrees of freedom of gravity at the Planck lengths? So wormholes, quantum foams, and that's true speculative physics. So here I would definitely agree. Now there has been a lot of progress in understanding systems of, non-perturbative systems of what one might call quantum geometry. So kind of the analog of what I'm talking about here in 4 dimensions, in lower dimensions, in 2D, starting with efforts to describe the non-perturbative dynamics of, in those days, still bosonic strings and their world sheets with an adequate method. And actually, this is really what lies in the past of the methodology I'm using now. So the origin is in 2D, where, of course, eventually one found out that, unfortunately, bosonic string theory is not a consistent theory, and one then had to move away from the type of regularization methods I'll be introducing shortly, which we're now using in 4 dimensions. So in higher dimensions, it's a largely uncharted territory. So I can even pose it kind of as a mathematical question. It's like, in some sense, these systems can be understood as statistical mechanics not say of spin systems or of, regularized QCD or something, but of geometry itself. So, and of course, there are crucial differences that come into play, as I have already highlighted. So one definite thing to say is that our classical geometric intuition is not a very good guide in what may happen here. Yeah. So unexpected things do happen in these concrete models we've been studying for the last few decades, and I give some examples later. So interesting questions, many interesting questions you can ask. So what aspects of classical geometry and gravity do survive, as I've already asked, and well, how do we explore this regime, really? Now, if you're familiar with, if you're a quantum field theorist, but also other people, of course, there's a familiar phenomenon that the dynamical variables you work with are not actual physical variables, but carry some kind of gauge freedom with them. So we have a similar story in gravity. Let me remind you of what this is. So how do we describe classical general relativity? Well, we model spacetimes as smooth differentiable manifolds. So I call that M. And here's again my smooth metric assignment G mu nu. Yeah, and this is very powerful and extremely convenient. And yeah, I mean, classical GR is a beautiful theory. Geometric properties of manifolds are encoded in everything that I get by extracting curvature properties from the G mu nu by taking up to second derivatives. So this is here to remind you of a huge redundancy that comes with this classical formulation. So here is my M, is my kind of curved manifold. So what I do in concrete cases, I introduce kind of a local coordinate system on this that enables me to do actual calculations. So it's so ingrained in us, yeah, that we don't often think about it, but it's really kind of an extra ingredient, kind of a handle with which I then control what happens here and with which I then write down my differential equations and solve them. Yeah? So it's a choice of coordinate system. And this choice is arbitrary. So Einstein's theory and any classical observable predictions I can extract from it don't care about coordinates. You can make them in you can do the computations in any coordinate system. So it's a type of gauge freedom, so which is a coordinate transformation, so which is a huge group of operations, also called diffeomorphisms of M, right? So classically, why don't you bother about this classically? Because classically, you think of it as a freedom, namely to choose appropriate coordinates to make your problem look as simple as possible. Great. In the quantum theory, it's nothing but a huge pain. Yeah? It introduces, of course, that's the simplest thing, it introduces huge extra degrees of freedom, which I have to kind of gauge fix typically, so to get rid of, because I only want, if I say take a quantum superposition, a path integral, I only want to take that over distinct physical configuration. So anyone who's worked on QED, QCD is very, very familiar with this as a problem, and of course cosmologists are also very familiar with this as a problem. So what is a key challenge, it turns out, in quantum gravity is somehow to implement the symmetry appropriately in the quantum theory. So I could spend a couple of hours talking about why this is immensely difficult and why so many things just don't work, but let me just say this as a fact. So what we want to do is describe physics, and again, a familiar theme from people working on gauge theory, in terms of observables, which by definition are objects that do not care, that are invariant under gauge transformation, in this case, coordinate transformations. So what happens in non-perturbative quantum gravity is you have to come up with observables. And we don't know about so many, totally independent of any approach. We don't know of so many. They tend to be very non-local quantities. So it's then difficult to work your way back to the physics. So what I however want to state is, you are familiar maybe with the idea of lattice gauge field theory. I say something about this on the next slide. So CDT does for quantum gravity in terms of really getting rid of these gauge degrees of freedom, the same as what lattice gauge theory does for QCD, but actually it's even better. in that there is not even a residual action of that group on the dynamical degrees of freedom as they are described there. So how does that work? Well, you have to put gravity or quantum gravity on the lattice. So this seems like very brute force, but you have to do it just in the right way. So what do I mean by this? So the general philosophy is that of lattice QCD, where lattice methods are the only available quantitative methods to allow you to say certain things of the non-perturbative regime of that theory. So here we're posing a similar question for quantum gravity, and I claim lattice, you should also do this with lattice methods, lattice gravity. So what is the kind of breakthrough that enabled all the beautiful development in lattice QCD? It's putting the degrees of freedom of QCD on the lattice in the specific way that Wilson wrote down in the 70s. So analogous. So this is your lattice, and your degrees of freedom of your QCD or whatever matter degrees of freedom. They live on a lattice, typically chosen to be just some hypercubic lattice. Now, what is the analog for geometry, for gravity? Well, since space-time is dynamical, it turns out the best way to put the thing on the lattice is not to, put it some form of G mu nu on a fixed cubic lattice or hypercubic lattice, but rather make the lattice itself dynamical. And really, the dynamics or the geometry of the lattice that are the degrees of freedom. So again, it's a longish story, but it leads to a kind of discretization of those degrees of freedom in terms of small building blocks with metric properties, from which you can derive all of their curvature properties in an approximate sense. And it goes back to an idea of Tullio-Regis, of course, well familiar to people here, which he came up with in '61. And it's a method to discretize the degrees of freedom of, in the first place, classical general relativity. What I want to claim, again, it's a longer story, that this idea is just so brilliant, but for the purposes of the quantum theory. It just takes care of the problem we have in the quantum theory of getting rid of the gauge degrees of freedom. And it's been vastly underappreciated because classically it never really took off. But it's really important and very foundational. So yeah. So I would claim, so this causal dynamic triangulation is just implementing these ideas. You get a non-perturbative, a background independent, and manifestly coordinate invariant path integral. But the lattices with which you regularize the series, the degrees of freedom, they are dynamical. And you are taking a superposition of kind of over all possible lattices. And that's the analog of doing the path integral over all curved smooth manifolds. Now, there is no fundamental discreteness hypothesized here anywhere, so you really should think of these lattices as a regulator, which you get rid of in the end, and you study continuum and scaling limits of this. So what is CDT quantum gravity now? Taking a somewhat larger perspective, I don't have too much time to talk about it, so I call it, it's a candidate theory of quantum gravity. So what distinguishes it? It uses a minimalist set of ingredient and prior assumptions. So these are choices you have to make, when you say, okay, here is my theory of quantum gravity, you have to say what are the dynamical degrees of freedom. So we are using basically metric degrees of freedom. You could say this is very, naive classical thinking, but you'll see that nevertheless, non-perturbatively, very interesting things happen. Very few prior assumptions, so no extra symmetries beyond those of the classical theory are assumed. No extra ingredients, no extended objects, no supersymmetry. So, it's again the idea, how little can I get away with still finding and deriving interesting results. So it uses, in terms of technology, only standard tools from quantum field theory, statistical mechanics, critical systems, so looking for phase transitions in kind of statistical mechanical models of so-called random geometry. So it's all familiar tools, and for any one of you who does not work on gravity, it should actually create a much larger interface to understand what's going on, because even in terms of philosophy, it's very close, say, to QCD or statistical mechanics models. Now, very importantly, we can do computations. So you may not, well, I've worked in quantum gravity for 30 years. So the importance of being able to not just write down things on paper and manipulate equations whose deeper meaning you don't understand on paper is to make a reality check and just put the thing on the lattice. Yeah? So this is immeasurably important because it gives you an idea of whether the models you're talking about have some chance of being interesting and correct, or don't even pass some minimal consistency checks. However, you don't see it if you cannot compute numbers. Even if your numbers have error bars and are, of course, subject to numerical uncertainties, etc. It's an immensely important piece of information which you do not want to deprive yourself of. It's been an uphill battle in quantum gravity to make this argument. And 30 years ago, you were just poo-pooed if you even, suggested touching a computer and putting systems like that on a computer. But this is changing, slowly but surely. Now, so I would even claim that, of course, we are in a very difficult situation in that we don't have phenomenology, direct observations to guide us in our building the theory. So this is really a kind of reality check that you're not barking up the completely wrong tree, as I said. So it's keeping us honest, and it produces some quantitative results. Yeah? It tells you something about the contents of your models, and that's not always easy to extract, of course, and you do need these non-perturbative methods to do it. In 2 dimensions, by the way, you can do certain asymptotic evaluations of partition function of path integrals analytically. So from there, you get also some confidence that the basics of the technology and the methods and the philosophy you're using are actually correct. Yeah? So that's helpful, but of course, it's totally different from the 4-dimensional theory, which is physically totally different and, of course, much, much more involved. Being a standard quantum field theory, as I've claimed, you have standard issues to deal with, which is that you have regulated the theory by putting it on a lattice, but when you send the lattice spacing to 0, of course you recover divergences, and you have to renormalize those. But you do this all kind of with standard methods. I'm not saying anything very much about the whole thing, and I don't have time for doing this, other than pointing you to 2 review articles. So this is 3 of my close collaborators, Jan Ambjörn from Copenhagen and Andrzej Görlich and Yuri Jurkiewicz from Krakow University. So we wrote this physics report together already quite some years ago. And earlier this year, I was approached by Classical Quantum Gravity to write kind of an update review. And this should hopefully come out soon. It's been online for a while. And I would also, of course, point out that you have a local group working on CDT. So this is Massimo Delia, one of the organizers, Giuseppe, and his other younger collaborators who are also working on CDT. So should you still have any open questions after my talk, please, and I have left, please pester them. Yes. Okay, let's come back to maybe a crucial question. So is it not a ridiculous presumption to claim to be able to talk about physics at the Planck scale? I mean, what is that supposed to mean? You saw this huge gap of 16 orders of magnitude between LHC physics and the realm I pretend to be describing. So isn't it just one giant free lunch at the Planck scale? I mean, can I just not dream up any Planckian theory and just claim this to be quantum gravity? Well, thank goodness it's not quite as easy as that, because one very critical thing you have to prove is that there is a correct classical limit. That means, again, if you zoom out, if you take some low energy, large distance limit of your theory, your candidate theory, it must match with what we know from GR to be already a perfectly good description of the dynamics of space-time on large macroscopic distances. Now, this turns out, however, is a criterion that's not easy to implement. Firstly, most approaches to quantum gravity simply cannot compute numbers. So you're never actually in the state to make any quantitative checks. As happened also with kind of the precursor of the causal dynamical triangulations, certain things just come out wrong. well, which is good, then you can discard them and move on. But for most part, many approaches are not sufficiently developed to even be able to ask the question, although they know it's a very important one. So because that's an issue of the classical limit in non-perturbative context. So it's in a way the emergence issue, right? I have some, wild Planckian dynamics of something or other, and somehow I must show here things emerge, like a four-dimensional space-time emerges, and it turns out typically your favorite way of describing little Planckian building blocks and gluing them together and making them interact doesn't produce anything remotely like this. That was a surprise for people working in the subject, but it's a general lesson. So what happens? What are typical properties of these dynamical systems? So we can do more in causal dynamical triangulations, and here just a very briefly. So what are we doing? So we're taking four-dimensional generalizations of triangles. They're called force simplices. Here's one of them, and by definition they are flat on the inside. And we glue them together in a nice way, so they are what is called piecewise flat manifolds. And they are nice models and approximation of classical curved manifolds, Lorentzian or after Wick rotation, Euclidean. So here is a piece of causal triangulation in 3 dimensions, because it's easier for me to illustrate. So here the basic building blocks are tetrahedra, and they carry, and that turns out to be a really important thing. So they carry all a light cone structure. So I told you they're flat, so they're just pieces cut out of Minkowski space. Now what turns out to be completely crucial in finding something non-trivial in terms of classical limits is to really give those building blocks a light cone structure, but then also have gluing rules that mean kind of the light cones change in a nice way as I glue one building block to the next. To impose on one of the histories that you will sum over in your path integral, kind of what is called a well-defined causal structure. So causal structure is, of course, a light cone structure, and it's a structure, of course, that is inherent in any classical Lorentzian space-time. Locally, you have a causal past, you have a causal future, you have light rays that move along null geodesics, etc. So you know at everywhere what it means to be causally related or causally unrelated of any 2 space-time events. So the same properties now we require our configurations in the path integral to have in this non-perturbative approach. And it turns out once you do that, you find beautiful results which you never found when you just thought of these as flat Euclidean. So that is what one called Euclidean quantum gravity. I don't know whether you're familiar with it. It's just ignoring the fact that there is a time, and there is are light cones, and there is causality, and just summing over kind of isotropic, kind of Euclidean type spacetimes. So this doesn't seem to work. This leads to instabilities in the non-perturbative theory. It's a long story. And currently, the only way we know around that is that of CDT. So imposing a causal structure in the a priori building up of the past integral histories that go into the quantum superposition. So if you like, it's an experimental finding that if you don't put this in, this causal structure, it's microscopic, you might say, then you don't get any interesting 4-dimensional universe out ever. So that's interesting. It tells us that apparently this causal structure, and with it some notion of time, they don't emerge from a theory where say you haven't put it in at all, that time exists and causal structure exists. So that's an interesting finding. Here's my path integral, and I'm running out of time, so I'm here. Anyway, it's a very formal object, so this is just the formal integral over all curved space-times, and you weigh it with the Einstein-Hilbert action. So basically, this is simple superposition principle. Of course, the crucial difficulty is to make sense of all the ingredients on the right-hand side, and CDT does exactly that. It regularizes things, and it makes sense out of this right-hand side in a regularization, and then you study the right-hand side systematically in the limit as you remove the regulators. So that is a familiar philosophy. Of course, to get there, it wasn't quite as direct and familiar. So What have you been able to show? What is a key result for why you should really take this seriously? Because it's the only approach that is able to do this. So from superposing, so quantum space-time, so configurations of the path integral, which individually, well, and morally speaking, look like this. They're just arbitrary gluings of these building blocks, whose geometry is very far from smooth or classical. So putting these without putting any kind of preferred background into it, just superposing all of these into this big path integral on the previous slide, we find that when we tune appropriately our Baire couplings, there's a whole region of phase space where these seemingly generate as a kind of a ground state or a state of least Euclidean action, something that has some properties that resemble those of a classical solution to the Einstein equations, and that's de Sitter space. So it's true emergence. So you have some microscopic degrees of freedom, and you are not putting in that it does only know about Einstein action, but this is very non-perturbative regime. So you have contributions from entropy, which typically spoil everything, this classical limit. But if you put the causal structure, if you require the causal structure to be there, then magically, if you look, for instance, if you evaluate the dimension of the space-time, you find that there is a region in phase space where macroscopically it becomes 4. And that's very non-trivial because you've taken a limit of things like this. So it's very non-trivial, and again, it's kind of an experimental finding which you would have never realized just looking at this path integral, just writing it down on paper. It just looks, whatever, if you don't understand what it is. So that is really an outcome. And then what has gone into the work since we realized there is this nice phase where some classical properties are present, it has gone into defining quantum observables to understand more and more properties of this kind of ground state. And of course, general properties have very little to do with classicality. So what you want to do is you want to measure quantum observables. We have just a few. We have kind of a shape observable which tells us the volume, the spatial volume of the universe as a function of time. Yeah. So, and I'll skip various things about, so this is typical, these are measurements. So this gives you some kind of idea. This is a phase diagram of the theory, and there are interesting phases where we are studying the physics, and we match the shape to a de Sitter universe, we match quantum fluctuations to de Sitter semi-classical fluctuations, and we measure the dimension of the universe. So what you should realize here is the dimension of the universe, kind of as a function of scale. It seems to be asymptotically compatible with 4, which is great for the classical limit. But when you go to short distances, it seems to be somewhere near 2. And we call that dynamical dimensional reduction. And it's a bizarre property that was first seen in CDT, but has since then been looked for and also found to some degree in other models of quantum gravity. So I basically cut my story short here. So this is just the bizarre thing about the dimension. So how can a dimension, go smoothly from 4 to 2? What kind of systems are those? Well, this is an example of a true quantum signature of what these systems seem to describe. And it's not captured clearly by a classical model. So something else is there on short scales. So just to summarize, so we are living in the century of gravity, as I claimed before, and quantum gravity is still an outstanding challenge. Non-perturbative quantum gravity can be studied just by putting it on a lattice, in close analogy with lattice QCDs, but a few crucial things that have to do with the dynamical nature of space-time have to be taken into account and treated correctly. And I would say CDT is one example of how you can do this. It's conceptually simple. So as I said, there are no extra exotic ingredients, which we do not already know from the classical theory. Nevertheless, since you allow very large quantum fluctuation on very short distances, very, very unexpected, interesting, and new things can happen. So we are making good strides on this towards a full-fledged quantum theory. It gives a very literal example of emergence, as I've emphasized, of classical geometric properties, one of the very few we have, but also we find true quantum signature, like this dimensional reduction. So we are working very hard on completing this. So this is very much a theory in work in progress. And of course, eventually we hope to predict observable effects from this. And we do think it's realistic, maybe even before I retire. So thank you very much.
Fascinating overview. There are lots of questions, I'm sure. I would say we take 2, 3 and postpone in view of the others to the discussion session. Ricardo.
Hello. Yes, so I'm not sure, I probably lost it in the talk. So will you be able to check that macroscopically Einstein gravity emerges, Newton law, the presence of just 2 elicited 2 long distance gapless modes? Will you be able to check this? Yeah. To see that this is gravity?
Yeah, so the proof, this is clearly what I showed you and where we are. This is clearly not the proof.
So you don't have a proof?
No, I don't have a proof yet,
okay,
but I have to, of course, to formulate all the questions you're asking in terms of suitable observables. That
sure. No, I understand the technical aspect. But do you expect it will be that or not?
I wasn't able to say much about it. We have this Feist diagram. So we have actually identified 2 second or higher order transition lines. So I would certainly expect, and of course I'm optimistic, that certainly along some of these lines, I find limits which then match up smoothly with classical.
So then why did you say in the beginning that you may also expect some non-trivial imprints at long distances? Where would they come from if these are the only degrees of freedom you would expect to have?
Well, they might come from, some non-trivial coupling, if you like, in the standard way of thinking of UV degrees of freedom, right?
So you think that in your construction you expect quantum field theory, effective quantum field theory, not to be the proper long-distance description, not to work? That's a humongous result, if it is true. So.
Well, one of the problems is that we cannot really very explicitly check up to what energies effective field theories should work, because we don't really have an approach.
No, I'm saying truly long distance. I'm asking long distance.
Yes.
Are you saying, do you expect that in this scenario, long distance description can be arbitrarily approximated by effective quantum field theory or not?
I guess the answer is yes.
So then why do you expect that there be deviations from what we know at long distances, like in dark energy or stuff like that? Yeah. Because once you assume effective field theory and you know the degrees of freedom, the description is unique.
But observables might be more involved quantities than we are currently considering.
Possibly short and to the point.
Yeah, very short. Actually, even more basic. I want to ask questions, but my problem is that you didn't give us anything. You didn't give us a theory. I don't see a theory. So what is your theory?
I had 45 minutes to sketch to you what I'm doing. Yeah. So I'm defining. The idea is I have a lattice theory, and I define the theory by looking at a suitable scaling limit of that.
But there's no theory. I mean, theory is something that consistent construction that correlates.
I think we will have a really interesting discussion session, but we will take one more short question.
When you said about the reduction of the number of dimensions, you meant the effective degrees of freedom, because if we take general relativity in 2 dimensions, it's just topological.
So I meant when we measure, it's very specific. I didn't have time to spell it out. If I measure, so I have a quantum observer that is a spectral dimension, which I can measure here. So I just study a diffusion process on this ensemble of geometries. And that I can use to assign a scale-dependent effective dimension.
So does it converge to a topological theory with this?
That is too early to say, but it's something that has spectral dimension too.
It's a fractal. It's a fractal dimension. So there is no smooth structure to it.
But you see, it could be an indication of many things. But I mean, effective dimension 2 is still a very wide notion. Mm-hmm. So we cannot say anything about the effective degrees of freedom as a Planck scale.
Yeah. Let's thank the speaker again. And there is an announcement by Dario.
Thank you. We should take a picture. So if you move here, we'll take a picture of all the participants. Please.
And then we have a break, and I think we start again at 11:20.
Okay, grazie. May you move here, please? Close to the table. Ma forse sentono, ci sono un po' di studenti che non sono registrati, allora magari si fanno scrupolo.
Dovremmo liberare più aiuti dalle griglie, se no.
Ah. Excuse me if I interrupt you, but you should take a picture.
Non importava nemmeno
Dario, invitali perché così si va giù.
Okay,
accendiamo quell'altra luce.
Sì. Concentrate. Let's converge. Please, if you come here,
So someone can also go on top of the table. Quelli però che sono dietro bassi bassi si variano avanti.
Quelli dietro bassi bassi. Quelli dietro bassi bassi.
Si devono sviluppare.
Why don't you come, Jeff? Because my pants are all wet from the rain, so I don't want to take a picture with wet hands.
I should be dried up now. He's coming.
Wow. Photoshop that in the water.
Cannot understand the meaning of a continuous dimension.
Yeah. I wasn't ready for this.
But then you took the chair.
I thought it was I was just worried about you. And you have
Sì, facciamo magari
And that so I go
Sì, Marco, dice avanti. Allora io intanto vado a
I don't know for how long, maybe a lifetime. Certainly for today.
She's also a good woman. I think she was comforting you. I was very good. Yeah. I was very good. You were in the hotel together. Yeah.
So she was worried.
No, I couldn't understand Italian, but I could actually see that the human exchange was really nice.
Okay. So well, but you risk to get wet, and so.
I get enough.
But when you said no, but Senti, potresti
Oh, well, it's no more than 20. Well, you have to carry on.
No, actually, it was nice. I didn't need to say it.
I didn't misunderstand it at all. I was not recalling your name. Does it make sense? Yeah. Oh, that's good to say something. What we hope
We can have just a coffee and then well, we are retired. Yeah. Because we have that's a long time. When Julia was born, but it's such a
hard as one of my competitors is trying to do his own experiment.
Ciao, sento la tua voce.
Ciao Monica.
Come stai?
Insomma, un po' under the weather, come dicono.
Under the weather, è tremendo.
Sì, vabbè, sono 2 settimane che sono sì. Ho preso l'influenza, non mi passa.
Non ti passa.
No. Tu come stai?
Bene. Bene.
Bene.
Questo è uno degli ultimi talk che voglio fare per un po' di mesi. Non ce ne posso fare.
Stai girellando un po', a parte che devi venire anche al video fra un po'. La prima settimana di novembre, mi sembra, una 4, mi sembra.
No, devo vedere.
Quindi ti sei arrivata ieri sera?
Sono arrivata ieri sera, sono soprattutto non era il cibo, era che tu eri in locale interno, tipo a casa tua che vedevi tratti, gli alberi, le palme, i cipressi, la torre e la basilica.
Così. Ho cose buone di questa città.
Sì, poi c'è un gran casino di treni, tutto.
Sì, c'è lo show. Ah, quindi domani sei qui tutto il giorno? Oh, mi piace. Io ho lezione domattina. Anch'io vorrei sentire la lezione domattina.
Io dico cose.
Vabbè, vai, vengo a sentire uguale, vado a prendere il caffè e poi torno qui.
Anche tu fai?
Oggi pomeriggio.
Tu cosa fai?
Io faccio Linda, sì, che doveva darlo uno studente di dottorato qui, ma lui ha preso, si è trovato una coincidenza per andare al Caltech una settimana, e allora tocchi io faccio io. Quindi io arrivo qui e dico io sono ambasciatore e non porto pena, quindi se avete domande eccetera scrivete a me.
No, infatti ci ho messo a prepararlo perché voglio fare un po' di LIGO, Virgo, Lisa. Vabbè, bene. Bene, sono contenta delle imprudenze, visto che facciamo dicevo due, ma quello del disco non lo so. Però, sai, per esempio, così sa che non può misurare. Se quello potrebbe essere una
Non lo so.
Però, no,
un po'. Perché secondo me i risultati pubblicabili 2 o 3 ci sono. Anche del disco, nel senso. Del disco, che non misuri.
Sì,
cioè,
sì, quella è una delle.
Uno lo può mettere in calce, diciamo, degli articoli, giusto per menzionare.
Sì.
Così uno evita in futuro di rifare il conto, ecco.
Sì.
Vediamo dopo, se poi penso quando andare a pranzo dopo, insieme.
No, non so se mi prende, ma oggi la Marilu è agitatissima per la storia di
Cosa è successo stamattina?
Ci è venuta a prendere, anche proprio, e diciamo una signora anziana ha attraversato la strada l'uno dell'altro, non sulle zebre, e ha dato, ed è caduta davanti a una macchina, è stata subito, però insomma, un bello spazio. Ma noi siamo, cioè c'era Zolla che doveva fare il blog. Era lievemente distratta perché stava guardando la signora che non so come si chiama. Una distrazione minimale, è riuscita a fermare tutto, però era.
Non l'ha toccata.
No, però non ha voluto andare, però sono andati all'ospedale a controllare via, chiamato l'ambulanza, tutto il resto, però io qui. No, perché tardi. Abbiamo fatto tardi per questo. io ogni tanto ci penso alle cose e poi metto di là, ma questa la devo dire, la metto lì in trasparenza, poi non so più che viene dopo.
Caffè?
Sì.
Ne fa poco.
Posso provare?
Sul Mac?
Sì. Io ho già attaccato.
Cosa ha attaccato? VGA? VGA significa che bisogna cercare il telecomando. Dove sarà il telecomando? Forse dentro l'editore.
Non so, forse potrei usare anche questo, però non l'ho mai provato, perché ce l'ho.
Ce l'ho l'uscita?
Cioè questa? Sì.
Vabbè, aspetta, ora stacchiamo questo, non importa, guarda.
Adesso vediamo se va.
Dovrebbe andare.
E poi per andare avanti e indietro?
Per andare avanti e indietro può usare o questo o questo.
Ma devo avere, non devo avere niente di
Dispositivo.
E questo?
No, questa è una pennina. Questo. Vediamo qual è, due.
Uno che cambia le slide e uno fa la luce.
Aspetta, che devo familiarizzare. Allora, io qui ho perso la presentazione.
Devo andare su ok. Però per attivare queste deve uscire da qua.
Devo uscire da lei, devo fare escape qui.
Sì.
Sai che cosa? Io c'ho un non Dopo solo me lo
Ma se c'è la presentazione può mettere direttamente sul PC.
Io ho una voce bassa e quindi volevo mettermi.
Proviamo?
Proviamo.
Proviamo.
Ora. Sì, si sente. Funziona, funziona. No, perché questo e quello, too many.
No, ma infatti questo è per le domande, perché lo portano in giro meglio.
Sì, ma questo è per le...
No,
I have mine. But we have to wait. It was really a bit of a shock, this accident, and so yes, also an old lady, and so
This one is in stress and
a lot of stress.
Yeah, Marilu should not have offered to drive you. She should have told him to take a taxi.
Yes, or to just walk, because in reality it's...
You would have been faster, probably.
Oh yes, in 20 minutes you are there. The only problem, it was really heavily raining.
Yes,
so
and not everybody has an umbrella.
Anyway.
she is still quite on the shock. So you're working on gravitational waves?
On the astrophysical interpretation, so my talk will be very astrophysical.
That's good, we didn't have that yet.
Okay,
very good.
That's so.
It's going to be difficult to chair this discussion session because it's three very different topics.
Yes. Very, very different.
Who knows?
Who knows? We'll see.
Let's see what comes out. So.
I think maybe we have to go outside to invite people.
Or close down for the call.
And maybe we wait 5 minutes.
Yeah.
Bene, bene.
Mi pare l'ultima volta ci eravamo visti a Berlino.
Ci eravamo visti a
meeting
Berlino.
3G.
3G, giusto,
Un
giusto.
anno fa circa.
Sì, non è tantissimo.
Perché a ottobre.
Se mi chiedono cosa c'è dentro in tutte quelle equazioni di stato, c'è un esperto, Ignazio.
La mostrerai.
Ma cerco di fare un overview.
Resti anche domani?
Sì, perché devo un po' anche lavorare.
Magari ci vediamo.
Sì, ci vediamo.
Perché io sono un po'. Alle 2 ho lezione, 2 ore, fino alle 4, quindi poi sono diciamo, un po' più libero, perché là mi devo rivedere anche un po' le lezioni, poi però se ci sei... Sì, va bene, io se no
dove? Io se
proprio sotto quell'angolino.
Ho capito. E semmai posso essere vicina anche a Walter del Pozzo.
Dove ti hanno dato un punto?
Perché devo lavorare con lui. No. Domani mattina voglio sentire la conferenza perché
sì, no, domani ci sono lezioni
gravity
dalle 9 alle 11 vabbè, comunque
I just, this is yours, if it is a Mac, okay. Okay. Can we shut down the light? Like this.
Please take your seats.
Please take your seats so we can start. It's a pleasure to introduce Monica Kolpi. She will talk about the gravitational universe.
Okay, good morning. Thanks for the kind invitation to talk about the gravitational universe, the universe that we will be exploring over the next decades by detecting the gravitational wave signals from a variety of sources in the aim at understanding more deeply gravity, and in particular gravity in the strong field and dynamical sector. From a century of electromagnetic observations from radio to gamma rays, we discovered that the universe is expanding from a singularity, the Big Bang, that we really don't understand fully since we don't have any consolidated theory of quantum gravity, and it is composed mostly by dark matter and dark energy, yet of unknown origin. But despite that, we know that gravity shapes the structure and the evolution of our universe and drives extreme phenomena as quasars that we believe are fueled by accretion onto supermassive black holes of million to billion suns, and for instance the short gamma ray bursts that are pinpointing places where stellar black holes of a few to several solar masses are forming in the universe. Our closest view to the Big Bang is the cosmic microwave background radiation, whose temperature anisotropies can be correlated with the fluctuation of the dark matter field, which during the dark ages they can grow to build up the first dark matter halos, which are hosting the first stars that are coming from the fragmentation of metal-free gas clouds, and we believe they will be forming at around redshift 20 when the universe is only 100 million years old. The formation of dark matter halos and their assembly continues, and optical observations and millimeter observation are telling us that galaxies are already in place at redshift 11, and the most distant long gamma ray burst is seen at redshift 7. We also know that a myriad of ultraviolet sources, ultraviolet sources are reionizing the intergalactic hydrogen. These are probably quasars, X-ray sources, or very massive stars. So the universe is fully reionized 1 billion years after the Big Bang. Then we know that the peak of the star formation occurred around redshift 3, and So the bulk of the stars in the galaxies were made at this epoch, and this is also coinciding with the peak of the quasar activity, accreting massive black holes that we see quiescent in the present-day galaxies. We believe that these supermassive black holes are indeed ubiquitous in these today's galaxies. Gravity has its own messenger, gravitational waves, and in my talk I would like to just understand how does the universe would appear if we would observe it in gravitational waves. The LIGO scientific collaboration and Virgo collaboration made more than two groundbreaking discoveries, the merging of two stellar black holes and two neutron stars. I will talk and describe them in a short while. And this is just the first glimpse into a universe which is really largely unknown, largely invisible, and that will give us a really complementary view compared to what we know from electromagnetic observations. Gravity is weak, space-time is stiff, and so the gravitational universe will likely select all loci where gravity is really extreme, violently changes space-time as around merging neutron stars, merging black holes of all flavors. So sources almost in binaries. And we know, and we already have a proof, that the waveform carry the exquisite information on the masses, spin, and the formability of these compact objects. Phase, amplitude, and frequency are really containing the bulk of the information, and quite unusually, also when we detect binaries, the gravitational signal carries also information on the luminosity distance of the source. And just to set up the stage, let me remind you that once you have a binary, we distinguish an in-spiral phase where the frequency of the gravitational wave is increasing, is twice the Keplerian frequency for a circular binary. So as the 2 point masses are spiraling and coming closer and closer, also the amplitude of the wave is increasing until the merger, when the horizons of the two black holes or the surfaces of the two black holes are touching. And then when you form a new Uralic star, it is vibrating toward a new equilibrium. And these two phases are extremely relevant in order to make progress in understanding gravity in the strong field regime. And just as a rule of thumb, near coalescence, the frequency, let me remind you, scales as the inverse of the total mass of the binary, and the duration of the last phases of the merger scales linearly with the mass of the binary. So we can understand that the gravitational universe has a huge extension in frequencies. We have the high-frequency gravitational universe, which is probed by terrestrial interferometers, advanced LIGO and advanced Virgo, which we know have detected many binary black holes and neutron stars. These are sources that have a frequency that peaks around 400, 500 hertz, and they are lasting only fractions of a second. We do hope that in the near future we might see the gravitational wave signal from a supernova explosion and also from the vibration of little isolated neutron stars. Then we have the so-called low-frequency gravitational wave universe, which will be probed by the Laser Interferometer Space Antenna, LISA, an ESA-led mission planned for the 2030s, which is aiming at detecting sources whose frequency is peaking around 1 millihertz. These sources can last in band for months, and the merger is consumed in hours. And when I'm thinking at the merger, these are the mergers of black holes of, say, million solar masses. We will also detect a background and individual compact binary in spirals, white dwarf spread all over the Milky Way, that I will not discuss, and extreme mass ratio in spirals that I will discuss later on. Then, to give you a complete overview, let me also mention that radio pulsars are really outstanding clocks with precision in 1 part to 10 to the 16. So if you have a network of, say, 50, 100 millisecond pulsars around the sun, they can detect a foreground of gravitational waves at nanohertz coming from the incoherent superposition of the latent spiral of supermassive black holes forming in galactic collisions when they are, again, still in spiraling and not in the verge of merging. But if you want really to explore the inflation where we might have a gravitational wave background, we have to rely on detecting the B mode in the CMB polarization. But as Chiara Caprini told you yesterday, there are other very interesting processes that can produce a primordial cosmological background, which is extending almost over all frequencies. But in my talk, I will mainly focus on space and ground-based interferometers. Gravitational waves, according to general relativity, are tensor perturbations of the metric of space-time propagating at the speed of light. They carry 2 independent polarization states. They propagate almost unimpeded from the source to the detector and just suffer cosmic expansion and lensing. And one of the key science questions that we will be able to answer in the next decade is really to understand whether the properties of the gravitational waves from real cosmic sources are the one predicted by general relativity, if there are other degrees of freedoms, other fields that really can really illuminate us on maybe dark energy and dark matter. There are key science questions with a very strong astrophysical touch. I would like personally to know whether the supermassive black holes we believe are powering quasars and most X-ray sources are really described by the Kerr solution, and how really gravitational collapse proceeds in a variety of cosmic environments. We would like to know if astrophysical black holes, if they are Kerr, we would like really to test the no-Kerr conjecture, which is asserting that astrophysical or Kerr black holes, so the space-time structure, the multipolar structure of space-time around black hole is uniquely described by the mass and the spin, which are responsible for the warping of space-time. We would like to understand if there are what we call black hole mimickers. This could be compact stars with a surface not very far from the Schwarzschild radius. Maybe they exist because, after all, we don't know how dark matter is and whether we have dark stars. And also we would like to know the state of nuclear matter under the extreme condition present in neutron stars. Back in 1974, the discovery of a radio pulsar in a binary hosting an unseen neutron star, a neutron star a double neutron star system orbiting with an orbital period of 7.8 hours, has demonstrated that this observation has demonstrated that the binary is shrinking by 3.5 meters per year because it is emitting gravitational waves. And this was an outstanding discovery because it was the first indirect evidence of the existence of gravitational waves, and the rate of shrinking of the binary was fully consistent with the prediction of general relativity. And I think that this was the main motivation to build a network of interferometers, advanced Virgo and advanced LIGO, with enough sensitivity down to 10 to the minus 23 in strain noise per root hertz, around several hundred hertz, in order to detect outside our galaxy the merging of these systems. We know a handful in our galaxies, in our Milky Way. All the masses of the neutron star are clustering around 1.3 solar masses. All will be merging in about 100 million years, so we couldn't wait that time, so we have to go and search for these extraordinary event in nearby galaxies. Let me remind you that neutron stars are the densest, smallest stars with a surface. They form in the aftermath of the gravitational collapse of massive stars of 20 solar masses, and they exist only up to a maximum mass whose value is not really well determined, say between 2 something up to 3 solar masses. This limit is set by a causality constraint that the equation of state of nuclear matter should be consistent with a sound speed less than the speed of light. And the reason of the existence of this maximum mass is that any additional source of pressure at microphysical level that we know becomes a source of gravity due to the fact that gravity is nonlinear, and the existence of this maximum mass has really key to evolve into the concept that stellar black holes should form if stars more massive of 20-30 solar masses are losing their stability. The reason of the variety of these many equation of states, this is the mass versus radius relation, is that we don't know whether in the inner core of these little stars there are hyperons, there's a Coulomb condensate to lower the energy state of nuclear matter, whether there is a quark-gluon transition. But if there are black holes of stellar origin, we think that we can see them either during their formation process, following detecting a long gamma-ray burst. We believe that a very massive rotating star, when it is collapsing into a black hole with surrounded by a disk, and the interaction with the disk with the spin of the black hole is launching a jet, which is also causing a collimating high energy emission. Alternatively, if you have 2 neutron stars in a binary whose total mass is exceeding the maximum mass of a neutron star, again, we expect that in the merger, we are going to form a black hole which is surrounded by the debris of this merger, which is launching a jet. This is a short gamma-ray burst. The discovery of 1708-17 has been really majestic this is the first and still unique source we have detected in gravitational waves. You see here the frequency of the gravitational wave rising during the spiral up to the merger that couldn't be followed by LIGO and Virgo because it was out of the frequency range of sensitivity. But what was amazing, and let me just remind you that recovering the gravitational signals has enabled us to determine the individual masses of the two stars. This is the posterior distribution of the component masses that are consistent with the double neutron star system we have seen in the Milky Way. But what was amazing was that 1.74 seconds after the merger, we see a very weak flash of gamma ray light that was able to confirm the connection of the merger with the short gamma ray bursts. And since the alert was sent all over the world, and since Virgo and LIGO were working as a network, they were able to localize the source with such a high accuracy that then astronomers were able to identify the galaxy and see also an optical sort of afterglow that I will discuss in a moment. But given the fact that we knew the luminosity distance from the signal with a given uncertainty, and we identified the galaxy, and of which we know the distance, then we were able to set very stringent limit on the speed of propagation of gravitational waves. And so this is really amazing. The merger was followed by a powerful kilonova emission in the optical, infrared, and ultraviolet, which was proving that when two neutron stars are colliding, as seen in this simulation, there are ejecta, which are extremely neutron rich, because after all a neutron star is a ball of neutrons, and due to the decompression of this matter, an R process nucleosynthesis started, and these light curves are just the outcome of the radioactive decay of these heavy nuclei that has been produced, and this also is a way to explain the abundance of heavy nuclei in our universe. The possibility of detecting such a bright kilonova is associated to the fact that neutron stars are deformed, and in the merger, indeed, they are tidally deformed, and theory told us that in the plethora of equation of state, a neutron star, depending on the equation of state, can have a wide range of values of the tidal deformability, which is a sort of the inverse to the fifth power of the compactness of the star. And you understand that when you have a merger, the more deformable is the star, more ejecta, more debris are produced in the surrounding, also an accretion disk, to produce a bright outflow. And for the first time, from the gravitational wave signal, it was possible to make the first measurement of what is called the effective deformability, which is sort of an average of the deformabilities of the two individual stars. So we could really discard a number of equation of state very stiff, and limit the interval of this lambda tilde below 800 and above 50 or so. So this really is the first step. So imagine when we will have many more of these events, so we can really make far more measurements of this parameter. And let me also show how beautiful is the result when you combine the information coming from the gravitational waveform. The tidal deformability enters to very high post-Newtonian order, so it's a very difficult measurement in terms of parameter estimation. But once you combine the gravitational wave signal with light, light is produced by the ejecta, and if the two neutron stars are not enough deformable, you wouldn't have any optical display. And so the fact you see light coming from this merger was able to set an upper limit on to set or reduce the interval of lambda between 800 and 400. So just an example to show that if we are going to combine both light and gravitational waves, this is the multi-messenger new astrophysics, we can really do a very nice job in knowing the neutron stars. Let me remind also shortly that since the galaxy was, the galaxy which was hosting this merger has been identified, this galaxy has a well-determined redshift, is part of the Great Attractor and has some peculiar velocity in addition to the velocity associated to the Hubble flow. But knowing the redshift from electromagnetic observation and the luminosity distance from the gravitational waveform, we had the first measurement of the Hubble constant. Certainly the error is far larger than the one from Planck and supernova, so we cannot really solve the tension between these two values, but this is just the beginning of what the gravitational wave astrophysics can do. And you know that LIGO and Virgo are now in observing mode, and in the public alert there is a claim of the discovery of a black hole neutron star candidate, so let us stay tuned. In late May we will know whether it is a real source. Then we had the discovery that you all know of the two merging black holes. I think this is really fantastic. You see here the frequency rising in time, which is associated to the chirp, that is the frequency increase associated with an increase in the strain of the gravitational waves, but we were also able to witness the merger and the ring down. 10 to the 65 ergs per second has been emitted in gravitational waves, 3 solar masses c² in energy has been released in gravitational waves. And what is amazing is that numerical relativity and general relativity can really recover fully this loud signal. So if there are deviations, we will know about these deviations from the talk of Walter Del Pozzo, but really it was really a majestic discovery. After the two observing run, we have the first ever catalog of gravitational wave sources from coalescing compact stellar binaries. This is the beautiful table. We have 10 black hole mergers. Just to really show that the gravitational waves really carry such huge information, let me just describe briefly. We can determine with an uncertainty of 20% the individual masses of the two black holes, the final mass of the new black hole that formed, and we have the first quite accurate measurement of the spin of the black hole, which is an extremely difficult measurement, astrophysically speaking. So we measure the spin, which is sourcing gravity from gravitational waves. And 0.7 is, yes?
Can I ask a question? This is the first question in the entire conference, in the middle of the talk, I think.
Great.
What is the units of the spin?
The spin is dimensionless if you normalize the spin by gm²/c³, because the Kerr metric is telling us that the spin cannot vary arbitrarily, while the mass of a black hole can be, classical black hole can be arbitrarily large, and it is confined with this one 0 and 1. 1 is a maximally rotating black hole. If this value of the spin would be larger than 1, you would have a naked singularity. And this 0.7 is really predicted by the fact that the new black hole is acquiring the spin from the orbit of the two black holes when they plunge at the innermost stable circular orbit. Here are the luminosities, which are universal, even two black holes of 10 to the 9 solar masses are emitting this luminosity. This is the radiating and radiative energy. This is the luminosity distance, which means that we have seen just the nearby sources, and we already have seen 10. These are the uncertainties in the sky localization, okay, which are still poor. And let me also show that we have been able to measure the sky effective. This is a sort of the combination of the individual spins of the two black holes projected on the vector of the orbital angular momentum, and apparently this spin is quite low, so probably the stellar black holes are not really spinning rapidly, or they are misoriented, and this is an information that astrophysical level, which I cannot comment, is extremely relevant. Let me also comment that we had discovered really a massive black hole of 50 solar masses, though there is some uncertainty, and it was sort of a surprise because the black hole we knew before the LVC discoveries were of this size, of about 7 solar masses. And we understood that these very massive black holes are forming probably at high redshift from metal poor environment, because the metallicity is really changing the mass. And this is really interesting because we really don't know much about the black hole of stellar origin. We believe that their mass can extend up to 40, 50 solar masses, as it was shown in this table, but there is a clear prediction that above, say, 50 solar masses, the very massive stars of, say, 200 solar masses evolve in their nuclei carbon-oxygen cores that are unstable to pair instabilities that are leading to the full explosion of the star. So no relic. So we have neutron stars, stellar black hole, no relics anymore. We certainly need a network if we want to pin down very well the position of the black hole mergers, because maybe there is some light, but apparently there is no light. They are so small, no gas around, no light associated to these, but also to make a measurement of the Hubble constant. If we have a very good localization, we can make a statistical measurement of the Hubble constant, having, say, 100 of events detected. So we need a network. Let me just mention that KAGRA, the Japanese underground cryogenic interferometer, will come online soon, and this certainly will improve a lot our ability to localize in the sky our sources. But the community is already thinking at the future, and we are thinking at the next generation of ground-based observatories. The two projects are called Einstein Telescope, which is European-led, and Cosmic Explorer, which is instead an interferometer which should be financed by the national, in US by the National Science Foundation. Let me just emphasize that the project will lead to a stepwise increase in sensitivity and bandwidth. If this is advanced LIGO, we will go down by more than 1 order of magnitude in strain noise intensity. So this, as you will see, implies a much larger cosmic horizon and also a wider sensitivity. So we aim at going down to, say, 3 Hertz. The reason is, and also to have sensitivity at the high frequency. At high frequencies, we would like really to improve the sensitivity, because as soon as 2 neutron stars are merging, they may form a black hole, but also an hypermassive neutron star which is vibrating. And if we catch up the longer-lived signal of these longer-lived neutron stars, we can really detect specific frequencies that can really tell us and probe the equation of state of nuclear matter. But if we go down in lower frequency, this is what we are going to expect to discover. Let me show this plot. I have two of these plots. Here I have redshift versus the total source frame mass of the binaries. And these are lines of constant SNR. These are the lines that we computed for Einstein telescope only. So let us notice that if you have, say, a black hole binary of 40 or 80 solar masses, I can see this binary up to redshift 15 during really the cosmic dawn, when the first stars are forming with a signal to noise ratio of 10. I can see the entire population of black holes through the cosmic reionization epoch, and also at the peak of the star formation rate, which is coinciding also with the peak of the formation of all the relic stars, so neutron stars and black holes. But if I look at the ability to detect higher masses, say binary with a mass of 500 solar masses, I still detect with a SNR of 20 or 50 during the epoch of cosmic reionization, black holes that we never seen, that we call intermediate mass black holes, that are relevant for what I'm going to tell you in a minute. If you have a network, you mainly see the entire universe, because your sensitivity is so high that in between 10 and say a few hundred solar masses, you see the entire population of binary black holes that live in our universe. Intermediate mass black holes are extremely important, because if you ask, how do we really know how supermassive black holes are forming? They are ubiquitous in all galaxies, they are part of our cosmic landscape, but you cannot form a billion solar mass black hole which has a radius of the size of an astronomical unit just from a single collapse. How can you make 1 billion solar masses inside such a tiny scale, on the galactic scales, of course? And so we have many astrophysical evidences that these very giant black holes form from what we call seed that fall in the intermediate mass range, say between 100 and 10 to the 4 solar masses. So if with Einstein telescope we will discover binary beyond the pair instability gap from very massive stars, we may have found the first seeds that they will grow by merging and accreting. Or maybe nature cannot set the condition for these seeds to grow up to the giant scale, and we need to envisage conditions where we have intermediate mass black holes that are coming from a collapse, which can be direct, but that it is extremely difficult to understand in terms of astrophysical conditions. So we have ideas of how these black hole seeds are forming, but the only way to discover them is to detect the gravitational waves that these seeds are emitting if they bind in binary. So if I am just taking you into the cosmological framework, this is our current view on how galaxies are forming from the density fluctuation of the dark matter density field. So they form filaments. At the intersection of this filament, baryons are falling, and you form at redshift 10 the first dwarf proto-galaxies that are then merging, forming the galaxies like our own Milky Way. In these sites, you have star formation, so formation of stellar black holes, formation of neutron stars, formation of seeds, and when accretion becomes very important, you produce the very massive black hole. So the idea that was the science driver for the space interferometer LISA was that as we go back in time, during the clustering of pregalactic halos, the black holes that form inside this halo can merge together when the halos are merging, just to account for the quasars we see at redshift 7 and the quiescent black hole we see in all galaxies of the universe. LISA is an interferometer in space, 2.5 million kilometers in arm length, and we know that with such an interferometer in space, again, in the redshift versus total mass of the binary, we will be able to detect black hole coalescences in the range between 10 to the 4 and 10 to the 7 up to redshift 14. And so we could really trace back the growth of the black hole to explain the quasars that are at redshift 7 and really have a complementary view on how galaxies and black holes are forming. This is almost my last figure. We carried on we constructed a semi-analytical model, which is sort of mimicking, which is describing the assembly of all these halos. So we follow as a function of redshift, which is the distribution of dark matter halos which are able to grow black holes. And in this plot, all these little dots are just pinpointing places where dark matter halos are hosting two black holes in the mass range, which is indicated here. And here are the curves of constant signal-to-noise ratio for LISA, and these are for Einstein telescope. So if we will have Einstein telescope and LISA operating together, we can really have a comprehensive view on how black holes are evolving really throughout the universe. But there is here a dip here, because when this white region is inaccessible both from ground and from space, and so if we will be able to construct an interferometer which with sensitivity, say, around 0.1 or 1 hertz, we can really cover the entire gravitational wave frequency spectrum. And let me sort of remark something I forgot. LISA, or we always say, is a mission which is signal dominated, because if we will ever discover many black hole coalescences in the mass range of 10 to the 6, which is the mass of our black hole in the Milky Way, we can detect them with an SNR of 500, 1000. So we will have enough signal in the rim down to make spectroscopy, that is, to measure the frequency of oscillation of the black holes, their decay time, to test Nennower theorem, and also to search for any deviation we would expect if there are alternative theories of gravity. So I hope I have convinced you that nature has been extremely generous with us. No, I'm going in the wrong direction, because as oh, well, I forgot this, but I don't have time. So as in particle accelerators, we can really learn about the fundamentals of the microphysical world. Nature has been very generous to create environments such that we can really detect the vibration of space-time in the violent mergers to really make a quantum leap in our knowledge of nuclear physics and the knowledge of the horizons, which are still really mysterious. Thank you.
Thank you very much for this interesting talk. I think in view of the advanced time, we would immediately go to the discussion session, and if you have questions to Monica, you can post them during the discussion session. The leader of the discussion session is Giancarlo Terra.
So, before starting the discussion, you know that this evening there will be an exhibition, but we need to know how much people are interested in doing that. So please raise your hand and I will.
What exhibition is that? Sorry.
It is the shape of the
It should not. No. It should be interesting in principle because there are a mix of arts and science exhibitions. So I don't know. Yeah. So please. Yeah. I don't know. It is on the program, so I assumed that you know about that. But it is organized by the European Gravitational Observatory. It is here in the center of Pisa, nearby, and we will have a guide. So we need to know how much of us are interested. So please raise your hand. 1, 2, 3, 4, 5, 6, 7, 7. Okay. Thank you. Oh, okay. So I think we can start the discussion session. First of all, I will invite the keynote speakers to come here. Renat Lowell, Peter Zoller, and Monica Colpi. Is not here also. And there was a large number of interesting suggestions, and I think also pending questions, so we can directly start if you want to come again to a question. Okay, please. Maybe, okay.
Hi, so I have several questions about the quantum gravity talk, but maybe I'll just restrict to two. One is, you didn't tell us much about what the actual observables are, so I would like you to elaborate a bit on that. And the second is, in this transition from 4 to 2 dimensions, do you see any relationship with the fact that, for instance, the string worldsheet is a 2-dimensional thing, and that's also a quantum gravity theory? Thank you.
Maybe you just. Okay, shall we use this mic? Okay. Yeah, observables. Yeah, unfortunately, I was a bit constrained in time. So we have a handful of observables. So, and this is really the general. I didn't put my slide on key important open problems. Maybe I should do this. So the first point is really finding more observables than we currently have, because we need them for basically all interesting physical questions we want to address. So be it existence of, a continuum theory that we hopefully see signs of addressing renormalization group flows in this scenario. making any link with phenomenology, hopefully and eventually. It all needs observables. So the observables we currently have, there are these very basic, you could even say pre-geometric things. So it's these dimensionalities. So it's a Hausdorff dimension of a space and the spectral dimension. So these two things have been very extensively studied. Even in pure math, you can apply them to very general classes of non-classical systems. So let me zoom in on the spectral dimension. This is just, you can define a spectral dimension whenever you can set up a diffusion process on the space. And as I said, on an individual piecewise flat space, like it goes into my path, you can do that. So you can also evaluate this quantity in the sense of expectation values on an ensemble of such things. Yeah. So that is one of our observables, and you can study it as a function of scale, or rather diffusion time, external diffusion time. But this is very rough. So in answer, someone suggested, so I'm combining actually answers to your two questions. So what does it mean if for this particular observable, I see that it continuously changes from on large scales near 4, or asymptotically clearly compatible with 4 within measuring accuracy, to something near 2. So where I should say, if I had presented the actual plot where we do the measurements and then show you the extrapolation, it has very large error bars. So, around 1.8. So very sizable error bars. So, but nevertheless, we do seem to see this phenomenon. So what does it tell us? Well, it's a dimension. So it doesn't tell us very much about local geometry. Of course, we know examples, say, of fractal spaces where the spectral dimension, of course, is constant. So by self-similarity, you can just, construct like recursive fractal spaces that have a spectral dimension of 1.487, blah, 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 blah. So we know examples of non-classical spaces that have non-integer dimensions. So what is it here? We are not quite sure what the origin is, apart from saying, clearly, it cannot be a classical, it's not well described by a classical space seemingly on short distances. So what can happen to 4-dimensional geometry when you start gluing these building blocks and you take a non-trivial scaling limit? Well, our fantasy is very limited, our understanding of what this truly is. And to enlarge our understanding, we need to look at more observables. So we have the spectral dimension, we have the Hausdorff dimension for this specific case, for the CDT. We have these volume profiles. So when I told you we see a matching to a de Sitter behavior of a classical cosmology, what I meant is the behavior of the Friedman, the scale factor, as a function of proper time, in the sense of expectation values, can be beautifully matched. It matches beautifully just the continuum curve of this volume profile, just for the classical cosmological solution. And not only that, but also the quantum fluctuations of the Friedman factor around that, the ones we measure in the computer, can be beautifully matched on, at least for the lowest eigenmodes, on those coming just from a naive kind of semi-classical continuum calculation you can do. So what that doesn't tell you is that this is de Sitter space. So because the volume of a space is a very rough observable. So what happens locally, there is no statement I can currently make that locally somehow this approximates, to some extent, a constantly curved space. However, I hope to be able to do that with this new curvature observable, so this Renyi curvature that I only mentioned in passing. So that would be a new observable. It is a new observable, and it's one that for the first time in some way relates to local properties which are linked to our classical way of thinking in terms of local geometry. So we have this notion, and we have evaluated it on 2-dimensional quantum gravity models. So this Renyi curvature, and it gives you a scale-dependent quantity that you can measure, and you find a plot like this as a function of scale. And for instance, we can evaluate this on dynamically triangulations or Euclidean and Lorentzian, and it seems to have a value. So, but that doesn't tell you much. It's apart from that fact, it's stable, and you can use it to associate quantitative properties with these systems, but you already a priori know there is no classical limit, so you're talking about some weird quantum spaces. So, but we're also in the process of evaluating it in 4 dimensions. And we hope to be able to say, look, on short, probably, well, there are two possibilities. So I know where, if I look at this quantum Ricci curvature, I know where I am measuring, I'm able, in my small quantum universes, they are on the order of 15, 20 Planck lengths across. I don't see a trace of classical behavior in terms of these curvature properties. That is a possible outcome. That could mean, anyway, all of this is completely wrong. It could just mean it's just too Planckian. So, yeah, so it doesn't even in an average sense, match well to a classical expectation. Yeah, but it also could be that at some, at 10 or 15 Planck lengths, I start seeing a resemblance of this particular observable with classical behavior, and that would be also very interesting.
Can you show us the Lagrangian?
The Lagrangian is...
Yeah, the Lagrangian that you're using.
Yeah, I'm using Einstein-Hilbert with a cosmological constant.
How do you know that that is the Lagrangian?
This is only the bare Lagrangian I put in.
No, but why aren't there other things? Why is this the Lagrangian? How do you know? Who told you?
No. Yeah. So
it's a serious question. Sorry.
Absolutely.
So this is at the basis of reductionism. You see something from far away. It's a point. Mm-hmm. How do you know it's a goat or just a tank, or I don't know?
Very good. So it is a good question, and it gets a serious answer. So the point is, we're talking about, this is a lattice model. So I'm putting in a bare action, and I'm starting.
Why is that the bare action? Why? Who told you that?
Can I please finish my argument? Okay, so I'm starting with a bare action, and I make the simplest choice I can start with. So of course, it's a question of how many parameters may I have to fine-tune in order to see something interesting. So what I do here, I start with the simplest possible choice, which has as 3 parameters basically G Newton and lambda. So I need a bare positive cosmological constant for this whole thing to work. So my philosophy is the following. So I'm then setting up this non-perturbative path integral. I see it has interesting behavior in a region which is very far away from semi-classicality, where I actually get contributions. So what is the kind of the action or the true Lagrangian that dictates the dynamics in this interesting region? It has contributions from the measure. So we're talking non-perturbative. Yeah? And it has contributions from the bare action that together conspire to a certain behavior, which I'm trying to analyze by evaluating certain observables and also by trying to understand how do things flow as a function of scale. So this is what I'm doing. So the philosophy is, it could be with just 2 tunable parameters, I'm not seeing anything interesting. But I am seeing something. But imagine, in a couple of years, we decide this is all dead. So then you would try and add, maybe the most natural thing would be, okay, let's add a higher curvature in the bare action. Of course, my complete action, my effective action, has, of course, all these terms. I mean, they're just generated during renormalization, to use a continuum language. So they are there in my version already, but not associated with tunable couplings. So, but if I had, as I said, if I banged my head against the wall, and did nothing more interesting would come out of that, it would be one of the things to try. However, let me say, there was this purely Euclidean precursor. So dynamical triangulations that I very briefly mentioned came out of studying bosonic string worldsheets in a non-perturbative way. So this turned out, when you tried to generalize it to 4 dimensions, to not, contrary to what people expected initially, apparently not to have an interesting classical limit, in the sense one never saw the emergence of a 4-dimensional space-time. And people then stood on their heads, turning screws, fiddling with the measure, the action, adding higher order curvature terms, but they never saw anything interesting. Actually, the kind of the universal properties are very strong, and even by modifying these ingredients, one wasn't able to find something that looked more interesting. So although we have a very limited understanding, say, of the universal properties of these higher dimensional systems of geometries, we have a little bit of experience. So it may be, many, of course, if universality works and is applicable in the way we hope it is.
I don't understand what you mean.
Universality means the independence of parts of the arbitrary regularization, the specific of the bare ingredients I used to set up my lattice theory.
Universality in the UV.
Yeah, the universality, that's right. Well, universality of the scaling limit of this theory. So that is the logic. Well, it is not up to me to tell. Yes.
Are you satisfied, or I guess not? But no, it's sort of to follow up, because I'm even on more basic level, because
you asked earlier a question.
Yeah, because I don't see any theory. Yes. You see, I don't see what the rules of the game are.
Yes.
And then you said, if this is dead, how can something that has no well-defined formulation or no well-defined rules can be even dead? You cannot rule it out. To rule it out, you must have a theory first. Well, and I don't see, I see a wish list. You say, okay, I want this and that. You all agree with that wish list, that, to understand gravity, the Planck scale, etc.
Yeah.
But you never described any theory in your talk. It was very general.
Yeah.
So what is your theory? What is the point?
My theory is, this is a gravitational path integral, which with nothing but...
This is definition of the path integral. Everybody can write it.
Let me finish my sentence.
Right.
In the presence of possibly the existence of a non-trivial UV fixed point.
Well, what does it mean? These are words. This is not a theory. This is wish. You may wish to have a theory.
Yeah.
You didn't show it. You didn't give us any equations. I listened to the talk extremely carefully. Sorry.
I'm glad she didn't give us.
No. Look. The equation.
What do you mean, general audience? You cannot substitute. Sorry. In science, we have to be concrete.
Yes.
You cannot be. Yeah. No. So because I need to know that you are not cheating.
Yes,
when you come up here and give a 1 hour talk, you have, unless you are concrete, I cannot tell any difference, because these are words that anybody can say.
That's right.
Sorry to...
Yeah, exactly. So what I should have shown you, I showed you the formal path integral, right? The formal dg e to the I.
Yeah, that's a definition.
Yeah. No, that's not a definition.
Definition of the path integral.
No, just stop and let me talk for a second.
Yeah, of course, I'm all ears.
So this is, of course, a totally formal object that everyone can just write down. So the second line that I didn't present to this audience is the exact prescription of what this becomes in the regularization I'm using, and which is a well-defined object, and a finite object with, of course, with a regulator in it. And it has certain bare parameters, it has a specific measure, and it's a specific prescription that actually enables me to put it on the lattice in the first place.
Yeah, but you see, I can only judge from what you told us. I cannot judge from what you didn't tell us.
That is good.
You said anything that could be a theory, you didn't tell us. You told us very general, things and stuff, we agree.
Yes.
But you see, I need to know that you are not completely wrong, even from the first step.
Yeah.
For this, I need something concrete. For instance, like Ricardo was asking about a correlator of the graviton and stuff like this, that you recovered something. For this, first I need to see what is your basic idea, what are the assumptions, what is the construction, and then the first consistency check, why you think that you are in a theory or in
Very good.
But you didn't tell us.
I told you some things that I saw. A general audience like the one here, of course, a talk like this involves a compromise.
In science, we have to be concrete.
Okay, but the basic idea of the meeting is to have, that it has to be a general meeting for a general audience. After that,
sorry, I cannot buy it from you.
After that, you have a specific question, and now we can try to.
And you are sorry. Let me disagree with you. I know that you are powerful as a chair.
No, I'm not powerful at all, but please.
We should not have a misconception about talk could be general. That's fine. I mean, scientific talk could be general.
No, general in the sense that we can try to communicate information between communities that are different languages.
That's not a communication of information. You have to be concrete. Otherwise, you are not communicating.
We are trying now to be as much concrete as possible. So,
but look, you know, people have very different backgrounds, and it was not the right talk for you. That I understand.
I'm sorry.
Yeah.
I am a professor of physics.
Yeah.
If you give
so am I. Yes.
If it's concrete,
yes.
I may not follow the details, but yes. I should be able to understand what you're talking about. And I simply don't understand what you're talking about.
Well, very good. You know,
That may be my fault.
No, it ends up in a compromise. I tell you, there is something very non-trivial behind this. And why don't you invite me and to give a talk at your institution? And I'd be very happy to talk about these things. Why are you shaking your head?
No, that's a different discussion.
That's a different discussion. I'm not sure.
Okay, let's move on because I don't see a clear conclusion about this issue. So, other.
Can I ask a question to Monica? Why can these very super heavy mass black holes not form from a cloud of stellar mass black holes, a very dense cloud, why is this not possible?
No, it's a very good question. Well, let me say that it's quite unlikely that a billion-sun black hole can form from the collapse of gas clouds of this size, because we don't see them, and you would imply radiative losses, loss of angular momentum to concentrate a mass, which is the typical mass of a dwarf galaxy within the size of our solar unit. So we need a process that has to go step by step. The only well-understood collapse, well-understood broadly, is the collapse which is leading to a stellar black hole. But we don't know whether stars, say, of 300 solar masses are going to form maybe in the very high redshift universe, where there is a lot of gas and no metals that are reducing, the absence of metal are reducing the wind loss from stars. But it is really true that you might have, and it was in my sketch, you might have really, you can imagine you are in a dense star cluster, you have stars that are forming, so they have big in size, bigger than on the main sequence, and so you start up a runaway collision. We don't see this in our universe, and this can lead to a black hole of, say, 300 solar mass, 3,000 solar masses, or we have direct collapse of a gas cloud, but the tendency of fragmenting as soon as there are even little metals, you are forming stars. So you need a gas cloud that has to be illuminated by a UV foreground which is surrounding the gas cloud to prevent this to fragment and let it collapse. There is always the issue of transporting out angular momentum. So it's very difficult to think at a realistic astrophysical collapse below 10 to the 5 solar masses. So around 10 to the 4 is really the maximum mass that I can let you consider astrophysically motivated, and then you have to let the black holes grow by mergers, but you double the mass. But to go to 10 to the 5, to 10 to the 9, you can't go by doubling the mass. You really have accretion in place. And we know that this is a good hypothesis, but we need seeds. And what I'm really enchanted is the possibility to think that either only stars can form black holes, and then you need the environment that help, or if there are really new stars, boson stars, that can form, okay, from dark matter that might have a dissipative channel that we do not understand, and this might be just in the middle of a galaxy. After all, dark matter is everywhere, And so we have to find these out. And we really don't know. So we have, the only way is mainly through gravitational waves, because the power of gravitational wave is to measure masses. Otherwise, a mass at redshift 5 would never be measurable. And so this is a very critical information that gravitational waves provide.
I have a question for Monica. From the gravitational waves, you see mostly the spinning black holes, as I understood. What about, but then you had the long gamma ray bursts that are from these black holes that probably aren't spinning so much. Is there any way to detect them with gravitational waves or something?
Nice question. Let me say about the spins of the black hole. The final black hole is always spinning because in a merger, because it's angular momentum. The black holes that prior to the merger that we see do not indicate that there are large spins, which for people like stellar physicists is very important, because they would like to know how much rotation is inside a very massive star, which is totally unknown. And also how rotation can affect the collapse of this core to form the black hole, and the neutrino emission that can launch or not launch a shock to form a neutron star or a black hole. The long gamma ray bursts are just a sub-class of high energy events that are long. They are lasting more than 10 seconds or so, because you are forming a black hole in a single isolated star. And the idea is that it is long because the gamma ray has to go through the envelope of the star, which is surrounding the collapsing core. So this is the reason why they are long. Then you have a debris, you have a disk probably, and the current model of long gamma ray bursts are requiring very high rotation, because you want to launch a jet. And in our perception of how jets are launched require a spin, and the direction of the jet is the direction of the spin. But there are models where you do not need a spin, but you need a disk, the angular momentum of the disk, and a lot of magnetic dissipation and not magnetic amplification. So it's really puzzling, because we are discovering that these black holes are slow-spinning, but they are just 10. The long gamma ray burst model require high rotation. There are galactic sources that tell that some black hole is really highly spinning, and there are plenty of models that can explain that. Let's go to measure and we see. But for the long gamma ray burst, you need a highly spinning black hole, which is not consistent with the one we see.
I have a simple question for Renato. Maybe I missed it, you already said it. Do you have just the Einstein-Hilbert Lagrangian in your path integral, or also matter content?
Oh yeah, very good. Yeah, so I didn't, so this is all pure gravity, I said. So it's straightforward to couple matter in the sense, so what is the easy way of doing it? For each copy of geometry, you just put a full matter system, and so you have a double sum over configurations.
Yeah.
So,
specifically, how difficult or not difficult would it be to put a localized source in your system, matter source?
Yeah.
Because that would give you an extra length scale to compare with.
Yeah. So of course, the obvious thing is kind of to put a massive particle in here.
Yeah.
So that raises, however, I mean, this is a longer discussion to cut it short. So we've been thinking about this for a long time. It raises various interesting issues. Firstly, the general issue for the matter coupling. So we are talking about Planck lengths. So what is it physically supposed to mean to talk about coupling to whatever, gauge fields, Moreau scale. So what are interesting observables one would study? We don't really know completely. So what would we expect if you put in a mass line? Now, so you see what I'm simulating here. These are wick rotated. So there is a well-defined wick rotation actually here, which I also didn't have time to talk about. So I'm talking about wick rotated ensembles. So what does it mean to put in a mass into those, and what is the Lorentzian interpretation? So we can do this, and we've done it. So it just becomes a mass line, and you can study its dynamics. And you see, if you make the mass parameter very heavy, then it deforms the geometry. But that is far from an interesting physical statement.
Well, like one then could address the question, do you recover the Newtonian potential at some distance? Or I know putting point-like masses in GR is impossible. You know, technically speaking, you cannot have a point-like source in GR.
Yeah.
So you would have to smear it in your lattice, whatever. But
yeah. So they're clearly technical issues since these universes are small, but they're more. Yeah. The more difficult, the bigger difficulty is to come up with a gauge invariant diffeomorphism invariant observable that would say, well, I have two particles.
Yes, you need two to see the attraction between them.
Yeah.
So the side question, how small is the universe in terms of the lattice space?
In the region where we've measured, I mean, we extract, a conversion to physical units by comparing semi-classical propagators of our volume fluctuation, just to say it's not a pulled out of a hat that we are identifying Planck lengths with lattice spacings. But as I said, these de Sitter universes, they are about 15 Planck lengths across.
Okay, thanks.
15. So they're extremely small, yeah.
I have a question to Monica. Sorry. So you mentioned some, you said some modified or more exotic changes of gravity. So how realistic is it to, so given other constraints, like let's say, I don't know, because there are pretty tight constraints on this kind of, on the solar system, and in the general modification of dispersion relation for the graviton is very tightly constrained. So taking those into account, is it still is it still realistic to enter in that window and probe something, or it's?
I'm not an expert in this field, but I can answer because I'm in a vast community that is addressing. Could we really see any deviation from GR from a gravitational wave signal? And as far as I understand, the most significant case is when you really are looking at the ring down of a merger, and you might have surprises because you won't fit with the frequencies that are expected from perturbation theory. And people are organizing to understand whether you might have a deviation, and if it is measurable. It is measurable when you have a lot of a signal in these last phases of the merger. And so you need really a close by and very loud sources, as maybe LISA has, or with Einstein telescope you might reach. And this is a lovely discussion. But as far as, so it is really the challenge.
No, of course.
Maybe Stefano maybe went there, but there are the possibilities. I'm very curious to know whether really the horizon that is.
Okay. So in other words, you see, there are sort of two directions. Normally, it's like one is to understand if there could be some quantum imprint of quantum effects from normal GR, like you don't modify it, just take into account quantum effects. And the other one is to really modify. To really modify. Yeah, I mean, to really modify, probably the solar system constraints and other constraints are so tight that I would be pretty it's probably hopeless. Now the question with whether you can have.
Sorry, if I can intervene. I think Enrico was not here. He mentioned that, for example, the deviation in just ring down physics could have been not more than 10 to the minus 4, 10 to the minus 3.
So large, you could have 10 to the minus 4.
No, it's large, but...
no, that's huge, because, I mean...
Suppose you have a glitch while you are looking at...
in scalar tensor. No, that's already constrained by solar system. No, scalar tensor, yeah, that you can probably constrain, and that's 10 to the minus 4 is sort of getting borderline. Right. Okay, so, yeah, so...
It's a possibility. No, it's an...
no, it's extremely interesting. I mean, that's the question is whether you can...
the broad community that by LISA will fly probably, and Einstein telescope will be built, we will have solved, is that we have plenty of waveforms for general relativity. And already, since it's a 15, it's a two-body problem with 15 parameters, it's already a mess. So you need huge templates in order, if you want really to make precision measurements.
Right.
And we don't have, for any other alternative theory, the same amount of bank templates that can recheck whether that theory is better than the other. And probably...
Yeah, well, okay, Ricardo is anxious, but let me just add, so, I mean, typically these so-called alternative theories, they boil down to some kind of scalar tensor story, because you have additional scalar degree of freedom, observation-wise.
Will tell.
Right, and that, I'm surprised that you are saying that's too complicated to have a template for that, because it's just one additional scalar, right?
I think Enrico showed work.
Okay, I missed it.
Maybe Walter can comment, that he's more expert than I.
So just to clarify, I actually come from the word that Monica was talking about. So the difficulty is that you cannot get accurate solutions that are non-perturbative in alternative theories of gravity. So I mean, nobody knows how an in-spiral merger in-down waveform looks like in a scalar tensor theory. There are a few numerical examples, but it's nothing that goes to the level of accuracy that we actually need to be able to dig out the signals from the LIGO Virgo data, because the problem of detecting violations of GR or detecting alternative objects, whatever you want to call them, it's always the same sort of problem. It's directly tied with the problem of estimating the parameters and detecting the source from the data, because we are in a noise-dominated kind of detector. Therefore, unless you have a template that is as accurate as general relativity, that you can really do a comparison, a one-to-one fair comparison, all you can do, and the strategy that the LIGO Virgo collaboration has employed, is to come up with phenomenological ways of testing whether something does not look like general relativity. So the problem is not solved, even because you don't know what the dynamics look like. Sorry,
can I make a comment? Perhaps the fact that you already know that this alternative theory should be very gentle and modify by a small amount ordinary gravity, perhaps it helps you in set up the computation just as a perturbation of ordinary. You don't need the exact solution, you just need a perturbed solution, right?
Yeah, but when you go to the nonlinear regime of the merger, you cannot really act perturbatively. I mean, already in GR, we don't know what the
additional degree of freedom should become sufficiently weakly not to give you but perturb you solve exactly any perturb.
So the point is, for instance, with the scalar field, it's not too difficult to go also pretty higher order in the post-Newtonian expansion. Now, I'm wondering of that figure that you showed. How long can I go with just post-Newtonian? So do I really need, how much do I really need to do the full numerical simulation?
I think that you need to go into the numerical simulation from 3M or 5M down.
You can get, say, to the last stable orbit, which is still far away from the merger. In frequency and time, of course, relatively.
If I try to estimate, for instance, the parameters of the merger, just with post-Newtonian, could I do it?
No.
Okay.
It's not linear.
Forget about you don't have the right dynamics. You have to do it with the numerics. Yes, you can follow the Rinda. So you can follow the in spiral. In spiral, you can test the post-Newtonian They are doing already in the Virgo collaboration. They are testing if the post-Newtonian terms are correct. But then it's also very difficult because in the post-Newtonian terms you have the mass ratio, you have the rotation, you have the tidal deformability. So it's a long, long story. It would be really a breakthrough and solve all problems if you would really detect a signal that has nothing to do with what we have seen. So, and there are theoretical models that produce, for instance, if you have two merging in boson stars, the signal is completely different. So, but then the problem is that if the boson star is not highly compact, the signal is really extremely, extremely weak. So maybe you don't have the sensibility, and you don't know whether you have sort of a burst that you don't know whether it is a burst from something else. So you need to dig it out into very much greater detail.
Sorry, I would like to get back just to make a comment, methodological and conceptual, on the issue of quantum gravity in a lattice approach. So all people working, I think the majority of people working on quantum field theory, particularly in this room, view the lattice as a very useful tool to reproduce the physics of systems where the dynamics is very quantum, it's quantum mechanical, if you want, non-perturbative in the far infrared. And the reason why it's so is that no matter what the details of your lattice description, that's what we do in lattice QCD, if there is a sufficient separation between your lattice length and the scale where the interesting physics takes place, it's universal, so you get robust results. Conversely, if you want to understand what happens in a system where the dynamics is non-perturbative in the ultraviolet, the lattice doesn't seem to be the right approach, because that's precisely, the point where the strong dynamics happens is precisely where you have the highest arbitrariness in the way you write your Lagrangian. So, and we know this truly explicit, the failure of the lattice approach, without even going to gravity, is well known in quantum field theory. We can present example of, say, generalized version of phi to the fourth, that are theories with phi to the fourth plus some gauge fields that have strong dynamics in the ultraviolet. They are not normalizable, precisely like general relativity. And you can try and go on for ages and ages and try to study their dynamics with the lattice. In fact, there have been people working on triviality of phi to the fourth. You cannot, it's worse than looking for a needle in a haystack. The number of possibilities that are in front of you are infinite. You don't know what Lagrangian you're using. And in most cases, you miss precisely what's happening. So for instance, I can offer to somebody working on the lattice a very simple Lagrangian that is known as a supersymmetric gauge theory in the free magnetic phase. It's a theory that looks very much like QED, where the dynamics at a certain scale become strong, very much like gravity. The growth is logarithmic, is not power law. And it's obvious that if I give this theory, the IR theory, description of this system, which is what you have in gravity from observation, you have Einstein plus cosmological constant, and you give it to somebody working on the lattice, there's absolutely no way the person will figure out what is the UV dynamics. We know the UV dynamics from Seiberg duality in this case, and there's no way to get it from a lattice description. So if this fails for very simple system like scalars and gauge fields and fermions, why should it work for gravity?
So let me comment about the issue of universality. So of course, what we study on the lattice, of course, the idea is that UV, so what I call Planckian physics, is large scale compared to the lattice spacing. So clearly, I don't trust results on the Planck length if my lattice spacing is of the order of the Planck length. So what I try to extrapolate, obviously via finite size scaling, is to get evidence where obviously I cut try to isolate between short distance lattice artifacts and, as usual, large scale effects, a region where I can trust the data. Yeah.
So can you study this theory I told you on the lattice and see whether you discover magnetic quarks and magnetic groups?
I don't know.
You will never find them. No matter what procedure you follow, whether you separate scales, there's no way you will ever find them.
Well, I'm studying a different system, and I gave you some idea of things. Obviously, it's clear it will be subtle to extract reliable results. Is that a reason for not trying it? I don't think so.
I have another question for Monica. One of the problems of gravitational waves is that we use templates, right? So can we really discover the unexpected if we use templates to discover gravitational waves? Or will the signal-to-noise be so gigantic in the future that we will no longer use templates?
Well, if the signal-to-noise ratio would be huge, you would probably won't need any template, and the wave is teaching you what is the correct theory, I guess. So it's a question that is circulating around, and so the problem is that maybe this will occur in an advance when general. So this new field will be in very advanced stages. So we will have very, but not for Virgo LIGO, and maybe not even for LISA if we are lucky. So, but instead the problem is if we would like to see a source with enough signal-to-noise ratio that has a shape that has no match with binaries. That would be already imagine.
Would we find this if you are just talking?
If it is really if it is really if it is really like the first source, it has to have an SNR of 30 to be secure and.
I'm sorry to interrupt this interesting and intense discussion, but we need to go to lunch. So we can continue later, of course. Thank you. Thank you to everyone.